Hi everyone, this video is a compilation of all of my Chapter 1 lectures from Chapter 1 in College Algebra and Trigonometry, the 4th edition by J.S. Rowdy, Marcus McWaters, and Leswaf Skrzipek. So this video is a compilation of all 7 lectures, but if you're looking for each individual lecture, each section's individual lecture, I'll post a link in the description to a playlist of each individual lecture. So again, this video is so long because it's a compilation of lectures. If you're looking for specific ones, it'll be in the description. I just have this one in case you want to try and digest it all in one very long form video. So thank you so much for watching, and let's get right into it. Hi everyone, welcome to Chapter 1. So Chapter 1 comes after Chapter P. Chapter P is kind of like a Chapter 0 because the name of the chapter is literally Basic Concepts of Algebra. It's just supposed to be a review of different properties we've talked about, like properties of exponents, factoring, stuff like that. Stuff that we will use for the entire course, and you'll use in almost any math course going forward. But what we're going to be more interested in doing is, instead of looking at these kind of out in space, so to speak, expressions that don't really have much of a purpose, what we can now do is solve equations and inequalities using things that look like that. Look like those expressions that we talked about in Chapter P. So what we're going to do in Chapter 1 is solve a whole bunch of different types of equations. And we're going to need to solve equations to answer things and answer properties of functions when we get to Chapter 2 and into Chapter 3. So we're going to start with talking about linear equations, where we just have equations with just a single x to the first power, nothing too crazy. And then we will extend that into quadratics in 1.3, where we now allow ourselves to have an x squared. And then we will do that in 1.5, which is in a separate file. But in 1.5, we extend it to be able to solve equations of almost any power using things that we already did in 1.1 and 1.3, and then some information in 1.2 and 1.4. What we'll do is then talk about solving inequalities, I believe in 1.6, and then in 1.7, we introduce absolute value into our equations. So lots of different types of equations. We're just going to go piece by piece. So let's get right into 1.1, linear equations in one variable. Okay, so an equation in general, an equation is just a mathematical statement saying that two expressions are equal. So we have some expression on the left-hand side, some expression on the right-hand side, and if we throw an equal sign in between them, this is now an equation, right? 7 minus 5 is just like an expression we could have talked about in Chapter P. Not a whole lot we would have done with it in Chapter P, but it is still just an expression. 2 is just a constant. Well, that was one of the first 2 things we talked about in the entire course in Chapter P. So saying that these 2 expressions are equal is an equation. Okay, but what we're going to be interested in this section is equations in one variable. So what an equation in one variable could look like is like 7 minus 5x. So as soon as we introduce an x, which we don't, 7 minus 5 equals 2 is very concrete. But the second we introduce an x, now we don't really know what x is. We don't know what it's doing there. So what we're going to do in this section is be able to solve equations with just one variable, x to the first power. So in general, we want answers that look like x equals some constant. That's not always going to happen, but for now, for this part of the section, we will say that is what's going to happen. For us to do that, we're going to use these steps. First things first, if we have fractions, we don't like fractions. We saw how messy fractions could get in Chapter P. So if given the opportunity, multiply everything by the least common denominator. In doing so, you see that all of your denominators go away, and that makes our job a lot easier. Simplify any parentheses or grouping, right? PEMDAS, stuff that we talked about, even though there isn't an e in exponents in linear equations, still, parentheses should always come first. The fewer parentheses, the better. So taking care of parentheses when we can is definitely of interest. Then we're going to combine like terms, which we did so many times in Chapter P. So we're going to combine like terms, and then our goal is to isolate the variable. So what we might have to do is, if we have like 7 minus 5x, we need to get the minus 5x term by itself, minus 5 times x. So to get rid of 7 minus 5x, what we can do is subtract 7 on both sides so that the x term is all by itself on one side. Well, once that x term is by itself, what we can do is multiply or divide by the coefficient. And just like that, we will get an answer that looks like x equals some constant. As always, what I'm going to say a lot in this chapter is to check your work. So now that we have equations and things to reference, it's a lot easier to check our work, right? When we're talking about simplifying a rational expression, there isn't really a way to check your work as opposed to just doing the problem again. But now what you can do is you can take your answer, plug it in, and see if your answer holds true. So let's get right into solving equations. Let's say we have 3x plus 5 equals 14. Well, we don't have any denominators, we don't have any parentheses. So what our goal is to get x by itself. Now, think about when we do PEMDAS. PEMDAS says do multiplication and division and then do addition and subtraction. What we're going to do is go backwards because we want x by itself. We need to go backwards. So if we have 3x plus 5 equals 14, what we can do to both sides is subtract 5. If we have plus 5, we can get rid of plus 5 by subtracting 5. But like we saw a lot in chapter P, we can't just subtract 5 on one side. We need to subtract 5 on both sides. If we apply minus 5 to both sides, as long as we stay consistent, we don't change the problem at all. So whatever you do to one side, make sure you do it to the other side as well. Okay, well, plus 5 minus 5, the whole goal was to undo plus 5. Well, you have 5 apples and you take away 5 apples, now you don't have any apples, and that was the goal. Okay, well, 14 minus 5 is 9, and now the x variable term is by itself, but it's not quite by itself. We have 3 times x. So when we had plus 5, we undid plus 5 with minus 5. Okay, and you could take a guess how we would undo 3 times x. Well, plus 5 became minus 5, 3 times x. What we're going to do is divide both sides by 3. So just like we had to subtract 5 on both sides, we also have to divide both sides by 3. We can't just do it to one side. That would really break the rules of solving equations. So we divide both sides by 3. And the reason we did that is because 3 divided by 3 is just 1. Well, we never have written 1x. So 3 divided by 3 is just 1, 1x. X equals 9 divided by 3, 3. And we like doing this. What I found a lot in my time teaching is that we don't really like dealing with just single expressions. You know, again, this out in space thing I keep saying. But the second that we're solving equations, we like this little puzzle of, okay, I subtract 5 and then I divide 3, and we get an answer that actually means something. Now, we don't need to check our work for every problem. You should check your work for every problem, but I'm not going to do it for every problem just for the sake of time. But if we want to know if x equals 3 is correct, plug x equals 3 back into the original. So if x is 3, 3 times 3 is 9. 9 plus 5 is 14. Our equation is true when x equals 3. Okay, so let's just solve a bunch of equations just like this. 7 minus 5x equals 2. Well, step 1, we need to get minus 5x by itself. Okay, well, we have minus 5x. That's what we need to get by itself first. We have this plus 7 to the left of minus 5x. How do we get rid of positive 7? We subtract 7. 7 minus 7 will go away, but we can't just subtract 7 on one side. We need to subtract 7 on both sides. Okay, 7 minus 7 goes away. That's the whole point. 2 minus 7, you have $2 and you spend 7. You are now $5 in debt. And now be very careful, because what you want to do is see minus 5 and go, oh, minus 5. Let me add 5 to both sides. But that's not what we want to do. Don't forget that this is minus 5 times x. Before, we had 7 minus 5x. This 7 was not multiplied or divided. It was being added or subtracted. So we subtracted 7. But to undo negative 5 times x, we need to divide both sides by negative 5. So again, please be very careful. because 7 minus 5x, 7 is being added, we have to subtract it. Negative 5 is being multiplied, we need to divide it. Well, negative 5 divided by negative 5 would just be 1. And same thing over here, negative 5 divided by negative 5 would be positive 1. Again, if we want proof if our answer is correct, plug x equals 1 back into the original. If x is 1, 5 times 1 is 5. 7 minus 5 is 2. Okay, so feel free to check these answers as we go. Of course, they're correct, or I wouldn't be giving a presentation on it, but it is still good practice to do because as soon as we get to somewhere around 1.5, we're really going to need to check our answers. Okay, negative 10x minus 12 equals 0. Okay, so we need to get x by itself. We see negative 10x minus 12. How do we undo minus 12? Well, in the last few examples, we had 7 minus 5x. Positive 7, we had to subtract 7 on both sides. But negative 10x minus 12, well, if we have minus 12, the undoing of minus 12 would be adding 12. But again, adding 12 to both sides. Okay, negative 12 and 12 go away. 0 plus 12 is just 12. And same thing, we have negative 10 times x. How do we undo negative 10 times x? We divide both sides by negative 10. Okay, negative 10 divided by negative 10 is just positive 1. That's the whole point, right? We just want to get x. It doesn't make sense to divide by 5. We would be left with negative 2x. 12 divided by negative 10, simplifying fractions. We've done that before. Okay, let's keep going. 2/3 x minus 3 equals 7. Okay, well, we have 2/3 times x minus 3. Well, we need to get rid of minus 3 to get the 2/3 x by itself first. How do we undo minus 3? We undo minus 3 by adding 3 to both sides. Minus 3 plus 3 is nothing. 7 plus 3 is 10. And now we run into a slight problem because all the other ones that we've had to divide by, we would divide by like 5 or negative 10. But now we have 2/3 and we would want to divide by 2/3. But don't forget that dividing by fractions is like keep, change, flip. And we kind of saw that keep, change, flip can be a lot of work sometimes. Instead, let's jump right to a better, more efficient way of thinking about this. When we divide by 2/3, keep, change, flip would say multiply by 3/2, right? Keep whatever we're multiplying by, or keep whatever we're multiplying, change the sign to multiplication, and flip the thing that you are dividing by. Okay, well, if we're dividing by 2/3, that would be the same as multiplying 3/2, right? Keep, change, flip. So a more efficient way of thinking about this is when we have a fraction on one side, why don't we multiply both sides by the reciprocal? The reciprocal of 2/3 is 3/2. But again, can't just multiply 3/2 on one side, need to multiply it on both sides. Okay, don't forget fraction multiplication. 3/2 times 10. 10 is the same as 10/1. Don't do 3 times 10 and don't do 2 times 10. 10 is 10/1. Okay, well, over here, 3/2 times 2/3. 3 times 2 is 6. 2 times 3 is 6. 3 times 10 is 30. 2 times 1 is 2. So we multiply by the reciprocal because we now get 6/6. And we know that 6/6 is just 1. The same thing happened, right? We wanted to get a 1x, and we got it by multiplying by the reciprocal. You could still divide by 2/3, but don't forget that when you divide by 2/3, that's keep, change, flip. You just got to be a little bit more careful. So multiplying by the reciprocal, just as equally correct. If anything, it's more efficient. Well, 30/2 is 15. 6/6 is 1. So our final answer is 15. Okay. I'll also take the second to note that if you can solve these problems faster than how I'm doing them here, that's totally fine. I'm teaching this with showing all the little pieces of what's really happening. I don't really expect anybody to actually show the step of multiplying by, sorry, of adding 3 to both sides. What you're more likely to do is jump from this line down to this line, and that's totally okay. Like I said, I'm just showing what happens in those steps. Okay, let's continue. 3 times 2 minus x plus 4x equals 3x. Well, PEMDAS, take care of parentheses first. So why don't we distribute 3? 3 times 2 is 6. 3 times negative x, negative 3x. Okay, well, we have multiple x's on one side, so why don't we combine like terms? Negative 3x plus 4x. If I am $3 in debt and I'm given $4, now I have $1. Well, we have an x here and 3 x's over here, so why don't we bring all the x's to one side? Well, we like to have our constant be away from the x's, so what I'm going to choose to do is subtract x on both sides. How do I undo plus x? By subtracting x on both sides. Plus x minus x just goes away. You have 3 apples and you eat one of them. Now you have 2 apples, and then we just divide both sides by 2. Okay, so fear not. It's okay to have 3 equals x. Just because it's not x equals 3 doesn't mean anything went wrong. 3 equals x, same thing as x equals 3. And now this is a really good opportunity to tell you you always have a choice of where you bring your x. I think a lot of people prefer having x on the left-hand side. So what you could have done here as well is subtract 3x on both sides and subtract 6 on both sides so that all the x's were to the left and your constant was to the right. You would get the exact same answer. It functions the exact same way. However, whichever one is more comfortable for you, by all means, go for it. Okay, let's do another ugly one with a lot of parentheses. Well, we got a parentheses inside a bracket, right? Brackets are just another way of writing parentheses. So why don't we distribute -2 first? -2 times x is -2x. -2 times -2 is +4. Okay, well, before we do anything else with this with this minus on the outside, why don't we simplify our inside? 3x minus 2x, 3 apples minus 2 apples, 1 apple. Okay, well, nothing else we can do inside the brackets, so why don't we distribute our negative sign and combine like terms? 6x minus x is 5x. Okay, and now we're just back to an equation we've been solving. Alrighty. Let's add 4 to both sides, and let's divide both sides by 5 to get x equals 3. Not so scary. Could always be worse, and it does get worse, but it's not so bad for right now. Well, let's do one more example, and I told you if you have a denominator, multiply by the LCD. And here's why. Well, what you could do is 2x over 9 plus 1 over 9 minus x over 6 minus 4 over 6. That's a lot of fractions. And we saw how much work just simply adding and subtracting fractions took. So instead of trying to deal with multiple fraction, addition, and subtraction, why don't we multiply everything by the least common denominator? Okay, what is the least common multiple of 9 and 6? What's the first multiple that they share? The answer would be 18. So what we're going to do is multiply everything by 18. Okay, literally multiply everything by 18. Okay, well, what we're going to do is distribute 18 to each of these two fractions. 18 times this fraction minus 18 times that fraction. This is like 18 over 1, so fraction multiplication. But notice now, we have 18 times something divided by 9. 18 times something divided by 6. Well, We learned in one of the very first few sections that we can simplify 18 over 9, and we can simplify 18 over 6. 18 over 9 is 2. 18 over 6 is 3. And now from here, not nearly as scary as it initially looked with fractions. Let's distribute 2. Let's distribute -3. We can combine some like terms. 4x minus 3x is just x. Positive 2 minus 12. You have $2. You spend $12. You are now $10 in debt. And last but not least, we only need to add 10 to both sides. Don't even need to divide everything by some number because x is all by itself. So that's solving linear equations. Not as scary. If it sounds like I overcomplicated it, but you can get the same answers, by all means, do it your way. It's totally fine. I'm just showing you what's really happening on the inside for a college math class as opposed to, high school taking things for granted. Okay, so, well, those aren't the only types of equations we can get. We can get other, like, weird-looking equations. So, what we had are conditional linear equations. Conditional linear equations just say that there's only one solution. When x equals 3, this equation is true. But that doesn't always happen. We have an infinite number of options for what we put on both sides. So we introduce two more types of equations. First one is an identity. An identity is any equation where the solution is all real numbers. Or in other words, no matter what you plug in for x, you will always get an equation that is true. And you'll see how that looks when we do an example in just a moment. We can also say infinitely many solutions, right? If we're talking about solutions, conditional only has one solution, but all real numbers would mean we have an infinite number of solutions. Likewise, we have an inconsistent equation, and an inconsistent equation is an equation with no solution. It means that no matter what we plug in for x, we can never get an equation that is true. So let's just do some examples and see where it takes us. They don't look any different from other equations, so you can't really think like, oh, this one's going to be an identity. We don't know. You'll see kind of quickly like warning signs of how these things would happen, but in other words, just solve them like any other equation. Well, we got a bunch of parentheses, so why don't we distribute this 2, and why don't we distribute this negative sign? Okay, we have some combining like terms we can do, minus 12 plus 5, and 12 minus 19. And now maybe here you already start to see something kind of weird. Okay, why don't we add 7 to both sides? And why don't we subtract 6x on both sides? We could divide both sides by 6. We get x equals x, but we still need to combine those x's. So let's bring all of our x's to one side by subtracting this 6x on both sides. However, when we subtract 6x minus itself on both sides, we get 0 equals 0. So your indicator that your equation is an identity is that you end up, after simplification, you end up with a statement that is always true. 0 equals 0 is always true. There is never a time that 0 doesn't equal 0. So what we got is something that says no matter what we plug in for x, we will always get the same value on both sides. Don't believe me? Plug in anything you want. Let's just plug in 0 to say, I don't know. 3 times 0 is 0. 0 minus 6 is -6. 2 times -6 is -12. -12 plus 5 is -7. Okay, so our left side is -7 when x equals 0. All right, well, when x equals 0, 6 times 0 is just 0. 19 minus 0 is 19. 12 minus 19 is also -7. Well, what if x equals 2? I don't know. Let's do something else, right? When x equals 2, 3 times 2 is 6. 6 minus 6 is 0. 2 times 0 is 0. 0 plus 5 is 5. When x equals 2, 6 times 2 is 12. 19 minus 12 is 7. 12 minus 7 is also 5. So we had two different answers, x equals 0 and x equals 2, that when we plug them back in, we get the exact same thing on both sides. So no matter what we plug in for x, we always get the same value on both sides. That's to say we have an infinite number of solutions. This equation is an identity. Okay, well, let's see what the opposite would look like. All right, lots of parentheses. Let's take care of this innermost one. Let's distribute 2. Let's combine like terms 3x plus 2x. And let's distribute this negative sign to 5x and negative 2. Well, we can combine like terms and say 5x minus 5x is, oh, that goes away. And we get 2 equals 1. However, 0 equals 0 is always true. But you're probably a little confused now because we're saying 2 equals 1. But 2 doesn't equal 1. 2 never equals 1. So what we got is the opposite, so to speak, of an identity. We got an inconsistent equation. We got an equation that no matter what we plug in for x, we will never get the same value on both sides. We will always end up at an equation that is never true. So in that case, we say there is no solution. Okay, well, a little bit short of an explanation because we went through all the explanation for an identity, and inconsistent is just the opposite. If we get an equation that after simplification, after solving, is always true, it's an identity, infinitely many solutions. If we get to a simplified equation that is never true, like 2 equals 1, that's never true. That's inconsistent. It has no solution. Let's do another 2 examples to see what happens. All right, lots of parentheses. Let's distribute 2. Let's distribute 5. Minus 5x plus 2x and 1 plus 14. 2x minus 5x. Lots of combining like terms. Maybe you already start to see something happening. Okay, let's subtract 15 on both sides. And let's add 3x to both sides. Right, we want to get all the x's to one side, so we need to add 3x to both sides. And we again get 0 equals 0. That is always true. No matter what we plug in, both sides will always be equal, infinitely many solutions. Don't believe me? Take any x value you want, plug it into the original equation, and you will see both sides are always equal. Okay, another one. Again, lots of parentheses. Let's distribute negative 6. Let's combine like terms. Let's distribute this negative sign. Let's again combine like terms. 3x plus 4x is 7x. Let's subtract 7x on both sides. And when we do that, 7x goes away on both sides, and we get 6 equals negative 1. And we are well aware that 6 does not equal negative 1. So we got to an equation that is never true, no solution. Okay. As a nice little summary, again, identity, the answer is always true, like 0 equals 0. So if you get 0 equals 0, 2 equals 2, negative 5 equals negative 5, that equation is an identity. It has an infinite number of solutions. Inconsistent, the answer is never true. It's like 2 equals 1. So if you get an equation and you solve it and it gets to something like 2 equals 1, negative 5 equals 3, whatever it is that doesn't make any sense, your equation is inconsistent. And conditional, there's only ever one answer, like x equals 3 or x equals negative 1, but we don't typically need to say conditional. Conditional is taken for granted. When we come to an identity, it's important to us that we can recognize an identity equation. It's important to us that we can recognize inconsistent. But when it comes to conditional, it's not as important to say it's conditional because we're just more interested in what is the answer, right? There isn't a concrete answer for 0 equals 0 or 2 equals 1 outside of infinitely many solutions or no solution. So in conditional equations, you don't need to say conditional. All I want is the answer. And in most cases, all your instructor would want is just what the answer is. Okay. And that brings us to formulas, or more specifically formulae, but for the purpose of what we're going to talk about, let's use formulas. Okay, so this is right here for you. But formulas in general are equations that show relationships between two or more variables. So what we've done so far is in a linear equation in one variable, but we know that almost any formula on the planet has more than one variable attached to it. So if we wanted to show a relationship between multiple variables at once, that is called a formula. So some examples: Celsius to Fahrenheit, Fahrenheit equals 9/5 Celsius plus 32. Volume, length times width times height. So just as an example, right, a relationship between two or more variables. Here, there's two variables, Fahrenheit and Celsius. So this would be a formula. Volume equals length times width times height. Well, that's four variables, so that is also a formula. So if we wanted to find out what 15 degrees Celsius is in Fahrenheit, what we can do is plug in 15 for Celsius, right? We want 15 degrees Celsius. We want to find it out in Fahrenheit. So let's plug in 15 for C. Okay, 15 over 5 is 3 over 1. 9 times 3 is 27. 27 plus 32 is 59. So 15 degrees Celsius is 59 degrees Fahrenheit. Okay, but we just did Celsius to Fahrenheit, and how would we go from Fahrenheit back to Celsius? Well, one option we have is to just plug in what Fahrenheit is and solve for C. However, that's not the most efficient. If I asked you, what is 20 degrees Fahrenheit in Celsius? And then I asked you, what's 40 degrees Fahrenheit in Celsius? And then 60 degrees Fahrenheit in Celsius? And then 80 degrees Fahrenheit in Celsius? Are you going to continuously plug in 20 and then solve for C? And then plug in 40 and then solve for C, and then 60 and solve for C, and so on? No, that's kind of inefficient. We would like to save ourselves some time. So a better method, a more efficient method, would be to solve for C first and then plug in Fahrenheit. So this is called solving for variables. Let's do an example of this. So let's solve the Fahrenheit to Celsius equation for Celsius. Well, what we're going to do is, even though we have two variables here, we want to solve for C. So treat everything else as a number. Okay, so Fahrenheit, I understand that that's a variable, but let's just treat it like it's a number. Maybe not a number that we can combine, but let's just treat it like a number for right now. Well, if we wanted to get C by itself, you would start by subtracting 32 on both sides. And then to get rid of 9/5, we would multiply by the reciprocal, 5/9. Well, 5/9 and 9/5, 45 over 45, that cancels out. Oh, and just like that, we've derived the formula for Fahrenheit to Celsius. So now, if I asked you what multiple degree Fahrenheits are in terms of Celsius, this is so much easier. Now you could just plug 20 into here and simplify, 40 into here, 60, 80, instead of needing to plug in 20 into here, and then 40 into here, and then 60 into here, and 80 into here, and continuously having to solve for C that way. So there is a huge benefit for us to solve for variables first, and that's not just for math, that's for anything. You might see in some of your biology classes or chemistry classes or physics classes that if you have to do multiple calculations of the same thing, maybe solving for the variable first can save you some time later. Okay, so one more example of this. Let's solve for the variable h. Well, we have an h here. We have an h here. If you're unfamiliar with this formula, this is the surface area for a rectangular prism, so a surface area of a box. But let's solve for h, which means if we're solving for h, treat everything else like a number. Maybe not a number that you can simplify, but a number nonetheless. Okay, think back to when we were solving equations with just x's. We wanted all the x's on one side. So if we're solving for h, let's get all of our h's on one side and all of our non-h's to the other side. Okay, well, we have an h here, but 2 length width does not have an h in it. So let's subtract that on both sides. Let's get that out of there. Now, not super obvious how we would combine 2 length height plus 2 width height, but what we do notice is that they both have an h in common. Well, think back to P4. If they both have an h, we can factor out h. Okay, last but not least, we have h times 2 length plus 2 width. Well, think back to when we were doing this for normal equations. If we had 6 times x, we would divide both sides by 6. Here we have h times something. How do we get rid of h times something? We divide both sides by that something. So 2L plus 2W over 2L plus 2W, those factors cancel out, and we're left with just this ugly looking formula for h. So maybe not so often that you would be, given the surface area and not the height, but just good practice for solving for variables. So that's the end of P1. So P1, like I said, just linear equations in one variable. I understand that this might have sounded a little complicated. Again, however you solved for equations in one variable in the past, whatever's easy for you, shortcuts you might use, they're all still correct. If you get the same answer and your work is just a little different, there's no way you can cheese these answers, right? Maybe some of them a little easier than others, but there's no way you can get to the right answer by doing the wrong work in most situations. So, like I said, too complicated. I get it. I'm just trying to explain it in as much depth as I can for a course of this level. So that's the end of 1.1. In the next section, 1.2, we're just going to do some applications of linear equations. Not a whole lot, just kind of like an exploration of some things. So yeah, I'll see you in 1.2. Bye. Okay, and welcome back to 1.2. I mentioned at the end of 1.1 that 1.2 is just applications of linear equations, kind of practicing some modeling, some exploration of things that linear equations can do. The things that we're able to do at this level, not a whole lot. We don't have a whole lot of tools, a lot of things. So our scope of what we can explore right now is kind of small, but just know that as we move forward, there's a lot of different things that these equations can do for us. So let's just look at a whole bunch of different examples of linear equations. So as a preface, all of these problems are very different. There isn't like a very set way of solving any one of these. It's kind of a little bit of thinking on our own, not so much like actual linear equations where get x by itself, subtract or add a number, divide or multiply by some number. Modeling in general is just kind of like thinking on your own. The only thing I can tell you is that if it helps you, draw a picture. But in most cases, you don't really need to do that. I shouldn't say that. In a lot of cases, you may or may not need to do that. So whatever works for you, by all means, you do it that way. But okay, let's just do a whole bunch of examples. Let's say a new refrigerator is on sale for $3,000. I have no idea if that's a normal price for a fridge, but let's pretend it is. So let's say a fridge is on sale for $3,000. If the original price of the fridge was reduced by 20%, what was the original price? We know the sale price and we know the reduction, but we don't know the original price. Okay. If the fridge was reduced by 20%, that means that we're paying 80% of the original price, right? 20% off doesn't mean we're paying 20% of the original price. It means we're paying 20% less of the original price. So if we have a 20% discount, it means we are paying 80%. Okay, well, if we say that x is the original price, we don't know what x is, but if x is the original price, then 0.8x is the 80% of that original price. So decimals and percentages, right? 80% would be 0.8. 8% would be 0.08, right? Practicing some percentages, right? That should sound familiar from a while ago. But yeah, so if X is the original price, then the sale price is 0.8X. Or again, 20% off the original price. Well, the sale price that we're given is 3,000. So if the sale price is 3,000 and 0.8X is the discounted price, then 0.8X equals 3,000. Well, we know how to solve for this. Divide both sides by 0.8 and we get 3750. So I know it might be kind of tempting to find 20% of 3,000 and then add it, but that's not correct. Because if you were to go backwards and take that new price that you came up with, 20% of that price is not the discount that we're looking for. So our original price is $37.50. 20% of $37.50 would be $7.50. So $7.50 off $37.50 would be $3,000. So please be very careful when we're practicing modeling these things. Okay, let's say that fridge was never reduced. What is the cost of the fridge, including tax? So I don't know where you're watching this, but let's assume tax in your state is a cool 6%, I guess. So if the fridge originally cost $37.50, we need to pay 6% tax on that $37.50. Okay, so we're paying the cost of the fridge plus tax on that fridge. Okay, so that means our total price is the cost of the fridge, $37.50, plus the cost of tax on the fridge, which is 6% of $37.50. Okay, well, 6% of $37.50 would be $37.50 times 0.06, right? 6%, 0.06. Okay, now this is going to be kind of weird because you could simplify this right away, but there is a little bit of a method to the madness right here. If they both have $37.50, can we factor out $37.50? Yeah, we sure can. If we factor out $37.50 from $37.50, we're left with 1. If we factor out $37.50 times 0.06, we're left with just 0.06. Well, 1 plus 0.06 is 1.06, and $37.50 times 1.06 is $39.75. So, assuming the fridge was never reduced, the total cost of the fridge with tax would be $39.75, including tax. So an extra $2.25 in just tax. So the reason why I wanted to show it to you this way is because I think it's kind of important for people to know how to calculate tax and total cost of items, right? You go to the store and it's like, this item is $39.99, and then you get to the register and it's a lot more than $39.99. Okay, maybe not a lot more, but it's more than $39.99. So in general, if you want to find the total cost of an item, you always multiply that item by 1 plus whatever that tax rate is in your state. So again, if your tax rate in your state is 6%, if you multiplied every item by 1.06, you have a really good idea on how much you would be paying for that item. So just a interesting thing you can do going forward. Or if you're trying to find I don't want to spend more than this, including tax, you can use that to your advantage. So we move on. A student wants her exam average to be an 85. On her first 4 exams, she got a 72, a 90, an 80, and a 67. What score does she need on the 5th exam to bring her exam average up to an 85? Okay, well, the average of her 4 exams would be adding those 4 exams together and dividing by 4. Okay, but we want the average of 5 exams, but we don't know what that 5th exam is. Well, that's not a big deal. All we want to find is the average of 5 exams, but if we don't know what that 5th exam is, why don't we just call it X for right now? So we would add those 5 exam scores and then divide by 5. Okay, but she wants her average to be an 85. So average will be 85. And would you look at that? This is now just another linear equation, right? X to the first power, linear. Okay, well, let's solve for X. Let's add 72 plus 90 plus 80 plus 67. That is 309. Well, we don't like fractions. Let's get the fraction out of here. So let's multiply both sides by 5. 5 times 85 is 425. 5 cancels out that 5. And now we can subtract 309 on both sides to get 116. So this student would need a 116 on her 5th exam to have an 85 exam average. And if we're assuming that every exam is only 100 points, it sounds like she will not be able to get an 85 average because you can't get a 116 on a 100-point exam. Okay. A equals P times 1 plus RT is the simple interest formula. And of these variables, P is the principal, the original amount you invest. R is the rate in decimal form, right? Like 6% would be 0.06. T is your time, which is usually in years. For this purpose, it's going to be in years. And A is your final amount. So if you start with some amount, you multiply it by 1 plus the rate times time, you get the final amount that you would have in your account afterwards. So let's say the account had 4440 in it after 4 years. Not put in 4440, it had 4440 after these 4 years at a rate of 12%. How much money was originally invested? Well, let's plug in everything that we know. A equals P times 1 plus RT. We're told that the final amount is 4440. We don't know what the principal is. We don't know how much money is initially invested. We're trying to figure that out. The rate is 12%, which would be 0.12, and the time is 4 years. Okay, well, all we need to do is solve for P. Okay, well, 0.12 times 4, 0.48. 1 plus 0.48, 1.48. And now we can just divide both sides by 1.48 because this is P times 1.48. 1.48 cancels out. 4440 divided by 1.48 is $3,000. So if you start with $3,000 in an account that pays 12% interest for 4 years, then your total amount at the end would be 4,440. Lots of fours going on here. Okay, another example, right? Kind of hodgepodge, they're a little all over the place. Find the length and width of a rectangle whose perimeter is 64 feet. Let me get my camera out of the way. Whose perimeter is 64 feet and the length is thrice the width, then minus 4. Okay, well, the perimeter of a rectangle in general is always given by 2 length plus 2 width. Okay, think back to when you first learned shapes. Perimeter equals 2L plus 2W. Okay, but we're saying that the length is thrice the width, then minus 4. That means the length is 3 times the width minus 4. So 3 width minus 4. Well, if P is 64, then let's plug in everything we know into this equation. P is 64, L is 3W minus 4, and now it's a linear equation for us to solve for W. Okay, let's distribute 2. Let's combine like terms. Let's add 8 to both sides. Let's divide both sides by 8, and we get that the width is 9. Now, that's not the end of the problem. We want to know what the length and width of this rectangle is. We have that the width is 9, but the length is given by 3W minus 4. Oh, we're using that equation that we started with. Well, length is 3 width minus 4. Width is 9. So 3 times 9 is 27. 27 minus 4 is 23. So the dimensions of our rectangle are 23 by 9. If we wanted to double check for ourselves, perimeter is 2 length plus 2 width. 2 times width is 18. 2 times length is 46. 18 plus 46 is 64. Alrighty, here we go. A group of office workers found that their salary can be modeled in this way, that their salary is 60,000 plus 700x plus 1850y, where S is their salary, X is their years of interning, and Y is their years of work experience. If one worker has been working for 2 years and makes 70,000, for how long did he intern? Okay, let's just plug in all of the information that we're given. We're told that this worker makes 70,000, so their salary is 70,000. 60,000 is constant. We don't know how long they interned, but we do know that he worked for 2 years. So Y is 2, right? Y is their years of work experience. They've been working for 2 years, so Y equals 2. Okay, and now we're just solving for X again. Let's multiply 1850 times 2. That's 3,700. Let's combine 60,000 and 3,700 for 63,700. Let's subtract 63,700 on both sides. And let's divide both sides by 700. So after 9 years of interning, 2 years of work experience, this employee makes $70,000. I don't know if 9 years of interning for $70,000 is a good deal, but so it goes. Alrighty, last example. This is a very popular question. It pops up quite a bit. There's another way of solving it if we use a section in chapter 8, but we're not in chapter 8, we're only in chapter 1. So let's see how we can do this. A store sells almonds for $4 per pound and peanuts for $2 per pound, but they want to create a 10-pound mixture that sells for $32. So how many pounds of each nut should they use? Okay, well, let's say that X is the pounds of almonds in the mixture. We have almonds, we have peanuts. Let's say X is the amount of almonds that is in the mixture. You could also let X be the amount of nuts, but it's going to end up being the same thing. Well, if we have X pounds of almonds and the entire mixture is 10 pounds, then there must be how many pounds of peanuts? This is kind of a weird question. It's probably the hardest part to the question, aside from actually setting up the cost equation. But if there are X pounds of almonds and there is in total 10 pounds, then there must be 10 minus X pounds of peanuts. So in total, there would be X plus 10 minus X pounds, right? The pounds of almonds plus the pounds of peanuts. Well, X plus 10 minus X, X's would go away, and we would get 10. So we know this makes sense. It's kind of weird that we're letting the amount of pounds be 10 minus X, but all it's saying is whatever space that we still have under 10 pounds is going to be dedicated to peanuts. If we have X pounds of almonds, then we have 10 minus the pounds of almonds for the pounds of peanuts. So it's kind of a weird way of thinking. I get it. We continue. Okay, well, if the almonds cost $4 per pound, then the cost of almonds would be 4 times X, the cost per pound times the number of pounds, or just 4X. If peanuts cost $2 per pound, then the cost of peanuts would be cost per pound times the amount of pounds of peanuts, 2 times 10 minus X. Here, we can distribute 2. 2 times 10 is 20. 2 times negative X, negative 2X. And then our cost equation would be the cost of almonds plus the cost of peanuts equals the total cost of the mixture. And what is the total cost of the mixture? Oh, it's 32 pounds. From here, now we're just solving for X. Okay, let's just drop those parentheses. They don't mean anything there. Okay, let's combine like terms. 4X minus 2X is 2X. Let's subtract 20 on both sides. Let's divide both sides by 2, and we get that X equals 6. So that means that we have 6 pounds of almonds in our mixture. Okay, well, if there's 6 pounds of almonds and the entire mixture is 10 pounds, then there are 10 minus 6 or 4 pounds of peanuts in the mixture. Okay, so you want a $32 mixture of almonds and peanuts. You need 6 pounds of almonds and 4 pounds of peanuts. So, yeah, very, very weird section. There's a lot of random information in 1.2, but that's kind of the idea. So, lots of information, kind of take them piece by piece. And with that said, we're going to change gears completely in 1.3 and talk about quadratic equations, which, if you're already looking at the screen, maybe just a tad scary, that thing right there. Don't worry, we're going to handle this thing together. So I will see you in 1.3. Bye. Welcome back for 1.3. So in 1.1, we talked about linear equations, and in 1.2, we learned to apply linear equations with all sorts of weird examples. But we're going to extend linear equations to now quadratic equations. So linear equations are equations that are just single x's, x to the first power, things that would create lines if we drew them. But quadratic equations are equations that are now in the second power of x. So what we're going to do in this section is a ton of x squared. So let's get right into it. Ax plus b equals 0 is a linear equation, but ax squared plus bx plus c, oh, this might look familiar from when we did AC method. Ax squared plus bx plus c equals 0 is a quadratic equation. Specifically, we want to make sure that a doesn't equal 0. If a equals 0, then we would have 0x squared, and 0x squared is just 0. So that would go away, and we're left with bx plus c equals 0. But bx plus c equals 0 is just linear, right? It would just have a single power of x. So specifically when a does not equal 0, unsurprisingly. Okay, we call ax squared plus bx plus c equals 0 standard form. And in a lot of cases, we want our equations to be in standard form. There's going to be one type of equation or one type of method of solving quadratic equations where we don't need to have equals 0. But in general, we want equals 0. So, for example, x squared minus 2x equals 3 is not in standard form. But if we were to subtract 3 on both sides and get x squared minus 2x minus 3, that would be standard form. Okay, so first method we're going to have to solving quadratic equations. Linear equations, they're all kind of the same thing, maybe just some added steps as you go. But quadratic equations have all their own steps and all their own methods with their own steps each. So the method that you use entirely dependent on the problem. Some methods work for multiple problems, and there's going to be a certain method, a certain formula that we have in later on in the section that will always work. But that doesn't mean it's the only method. So the first method we're going to talk about is factoring, right? In P4, we spent a lot of time factoring, and we're going to apply that here to equations. So our steps is put your quadratic equation into standard form. So get equals 0 on one side. Get everything to one side. Once you have equals 0 on one side, factor the other side. So whatever side that you bring everything to, probably the left-hand side, factor that side. What you're then going to do is set each factor equal to 0. And you're going to solve each factor. So let's explain why. When you have something factored, right, some factor times another factor equals 0. Well, we're saying that we have two or more, two things that when you multiply them, they equal 0. Well, what's the only way that two things can multiply to 0? The only way that two things multiplied equals 0 is if at least one of those things is equal to 0, right? 2 times 4 is never going to equal 0. However, 2 times 0 will equal 0, or 4 times 0 will equal 0. So when you factor, what you're going to do is set each factor equal to 0 and solve each of those factors. And then, like I said in 1.1, check your answers. Not going to happen, not going to need to be much of a worry here in 1.3. But again, I want you guys to get into the habit of checking your answers because come 1.5, you will need to check your answers. Okay, so let's do 2x squared plus 5x equals 3. And step 1 says, bring everything to one side. Get to standard form. Well, we have equals 3. If we want to bring this 3 over, all we need to do is subtract 3 on both sides. Okay, so 2x squared plus 5x minus 3. This is factorable. And we spent an entire section factoring things that looked like this. So I'm not going to go over the factoring here. If you're looking for that video, that would be section P4. I can link that into the description. But please go practice factoring before you try and understand the factoring part here. That or just take one of the methods that we do later on. So 2x squared plus 5x minus 3 factors as 2x minus 1 times x plus 3 equals 0. Okay, and here's what I mean. Notice that we have two factors that are being multiplied together, and when we multiply them, they equal 0. The only way that these two things can multiply to 0 is if at least one of those things is 0. So what we're going to do is set both of them equal to 0. If this equals 0, 0 times x plus 3 is 0. That would satisfy our equation. If x plus 3 is 0, then 2x minus 1 times 0 is also 0. That would also satisfy our equation. So set each factor equal to 0, and what you now see is these are just a pair of linear equations. Add that, very nice, easy linear equations. This, add 1 to both sides, divide by 2. Here, just subtract 3 on both sides. So what we get are 2 answers. One thing that makes quadratic equations very different from linear equations. Linear equations, in most normal cases, we got one single answer, x equals 3 or x equals negative 5. But for quadratic equations, what we're going to get a lot of the time is 2 answers. 2 answers, very normal. We will look into situations of how we know what those 2 answers are going to be, what type of answers we get. But for right now, not going to think about that. So it's very normal and it's very okay to get 2 answers for quadratic equations. If you want, go back in and check each one. Just as an example, let's just check negative 3. Well, negative 3 squared would be 9. 2 times 9 is 18. 5 times negative 3, negative 15. 18 minus 15 is 3. And the same would be true for 1/2. 3x squared equals 2x. Again, we need to get one side to be equal to 0. So let's subtract 2x on both sides. Okay, well, no number this time. And if anything, this is a lot easier to factor. We can factor out just an x. And now we have x times 3x minus 2 equals 0. These are still 2 factors being multiplied to 0. One of those factors is just plain x, and that's okay. So we're going to set x equal to 0, and we're going to set 3x minus 2 equal to 0. Well, if anything, this actually made our job quite easy. X equals 0 is already done. 3x minus 2 equals 0. Add 2 to both sides. Divide by 3. So again, we get 2 solutions. So that's quadratic equations. It's nice when they boil down to linear equations almost immediately. Just a little bit of tinkering, just a little bit of factoring makes our job a lot easier to deal with. Okay. X squared plus 16 equals 8x. Well, let's subtract 8x because we need to get 0 on one side. And this factors quite nicely to x minus 4 times x minus 4 equals 0. Okay, same thing. Set each factor equal to 0. But what you notice is that we get x equals 4 twice. Well, for now, we'll talk about what that means to get the same answer twice. But that's in chapter 3. This is chapter 1. your final answer is just x equals 4. There's only one x that satisfies this quadratic equation. So the two previous examples, we have two x's, two answers, two solutions, and now we had only one, and that is, again, totally fine. It doesn't mean there's anything wrong with the equation. There's nothing wrong with your work. It is possible that you get only one solution. And again, at the end of the section, that's when we'll discuss how we get a certain number of solutions and what type of solutions. So we like the method of factoring a lot because factoring is easy, right? In comparison to other things we're going to talk about, factoring is very familiar to us and we know how to factor. But not always is it going to be the only option, right? We're also going to talk about this thing in just a wee tad, but in general, we need a stepping stone to that. So square root property and completing the square are going to be some of your least useful methods because you're probably always going to want to go for factoring or quadratic formula, but it is a good stepping stone to what we talk about, and when it works, it's kind of nice. So let's talk about square root property first. Square root property can be used if the factored side is a perfect square, and what I mean by that is something like x plus 2 squared. That would be a perfect factored square. So the other nice thing about square root property is that the other side doesn't need to be equal to 0. In factoring, one side has to be equal to 0 because we need to be able to set each factor equal to 0 separately. But for square root property, we're not going to need that to be the case. We're going to need equals 0 for quadratic formula, but for square root property, we do not require that. Okay, so in general, if u is some algebraic expression and d is some number greater than or equal to 0, so some expression squared equals some non-negative constant, what we can do is take the square root of both sides. Just like in linear equations, when you add 5 to both sides or divide both sides by -2, you are allowed to take the square root of both sides. However, when you do that, when you take the square root of both sides, what you need to pick up is a plus and minus. You are allowed to take the square root of both sides so long as one side gets a plus and minus. So the reason for this has to do with the square root of u squared, right? We said square root and that squared cancel each other out and would be absolute value of u. But we haven't talked about enough properties of absolute value to prove that right now. However, that does reappear toward the end of the chapter. We're just going to kind of take it for granted for right now. So if u squared equals d, you can take the square root of both sides to undo the squared, right? How do you undo plus 5? By subtracting 5. How do you undo u squared? By square root of both sides. However, when you take the square root of both sides, you need to get plus and minus. I also want to stress this is only for when we are solving equations. Think back to chapter P when we were just looking at random radical or root expressions. We don't magically pick up a plus and minus when there is no equation to solve. This is only used when we are solving an equation. When you take the square root of both sides, that is when you pick up plus and minus. Okay, so x squared minus 3 equals 0. How we would do this before via factoring is a little different. How we would factor this is say, oh, this is a squared minus b squared. Well, difference of squares, a squared minus b squared, a plus ba minus b. You set each factor equal to 0, and you get x equals positive square root of 3 and x equals negative square root of 3. But this is really uncomfortable because this isn't nice. Saying that 3 is square root of 3 squared and we have to factor it that way, that's not necessarily very helpful. So here's where square root property comes in. Instead of factoring something that isn't as naturally factorable as other things we've talked about, why don't we instead add 3 to both sides. And now our expression side is a perfect square. It is literally something squared. When we have something squared, we can undo squared with the square root. Again, however, when you take the square root of both sides, you need to pick up a plus and minus. So square root of x squared, well, that undoes the x, but on the other side, you need to get plus and minus the other side. That is really, really, really important. So a little bit quicker, a little bit more, a little easier to picture. Okay, let's do another example where it's not just x squared, right? X squared minus 4 equals 0. You can kind of see like, oh, 2 and negative 2. But what if we have something like x minus 7 whole thing squared? Again, this is a great example of something squared, and that would be our giveaway to take the square root of both sides. But again, when you take the square root of both sides, you need to pick up a plus and minus. Okay, square root and the squared cancel each other out. That's the whole point. Square root of 9 is 3. So we get x minus 7 equals plus and minus 3. Now, this is a really good step, and if you can get here, you did the hard work. However, our answer should be x equals one single thing. So we now need to do x minus 7 equals positive 3, and x minus 7 equals negative 3. And again, you're starting to see the pattern for quadratics where we're always going to get 2 answers. Let's add 7 to both sides. For each problem, add 7 to 3, we get 10. Add 7 to negative 3, we get 4. So we again get 2 answers. And that's square root property. One more example. X minus 3 squared equals 5. Again, this is a perfect square. So let's take the square root of both sides. And again, when we take the square root of both sides, we get plus and minus on the other side. Square root and squared cancel each other out. So we get x minus 3 equals plus or minus square root of 5. This is not nearly as pretty. So why don't we just add 3 to both sides? Now you might be wondering, why don't we do it separately? X minus 3 equals positive square root of 5. X minus 3 equals negative square root of 5. It worked nicely in the last question because the answers were very easy to simplify. But in the case of square root of 5, not really. You could say your answers are 3 plus square root of 5 and separately, comma, 3 minus square root of 5. But this answer is nice and simplified as well. Or not nice and simplified. It's a nice simpler way of writing that. Also, you'll note that I don't use decimals in a lot of situations because in general, decimals aren't necessarily always exact. For example, if you plugged in 3 plus square root of 5 into your calculator, you would get a really ugly irrational number that at some point you need to round. So instead of doing the extra step of plugging this into your calculator and rounding, why don't we just say the answer is 3 plus square root of 5 and 3 minus square root of 5. So for those of you that are taking my class, I love this answer right here. You give that to me, we're all for it. But from course to course, you might be told to do decimals, or you might be told to write your answer separately, whatever works. So if it can be simplified like the previous question, simplify it. If not, it's okay. Let's do one more example. 9x minus 5 squared minus 49. Well, the left-hand side, as it's written, is not a perfect square, right? 9x minus 5 is a perfect square, but minus 49 doesn't make this factor as nicely. So what's the remedy? I'm going to just add 49 to both sides. Well, now this is a perfect square. We can take the square root of both sides, make sure we add our plus and minus to the other side. Square root and squared cancel each other out. Square root of 49 is 7. So now we have 9x minus 5 equals positive 7. 9x minus 5 equals negative 7. This is just a pair of linear equations, and we get 2 answers. I haven't made it clear before, but also we like to write our answers in numerical order. So for example, negative 2/9 is before 4/3 on a number line. So writing x equals negative 2/9, comma 4/3 is a really nice way of summarizing your answer. You could, in theory, just leave your answer as x equals 4/3 and x equals negative 2/9, but we like to simplify things. Okay. If our quadratic is not a perfect square, what we can do is make it a perfect square, and that's called completing the square. This is a weird method for solving equations. I don't think many of you will use it all that frequently, but it is technically needed to broach the topic of quadratic formula. So let's do that. This can only be done if a equals 1. So ax squared plus bx plus c equals 0. We need to make sure that a equals 1. Because if a doesn't equal 1, it's a little bit more difficult to try and picture. So just be careful for that. Steps to do this: move your constant term away from your variable terms. So you have an x squared term, you have an x term, and you have some constant. Move your constant to the other side. Okay, the part that makes completing the square is that we're going to add b over 2 squared to both sides. Now, that seems like kind of a silly step. However, when you add b over 2 squared to both sides, what that allows you to do on your variable side is factor to just x plus b over 2 squared, and the right side, well, we move the constant to the right side. We added another constant to the right side, so the right side is just a constant. Well, we now have a perfect square. We now have a constant. It's just square root property from there. Okay, so let's do an example of this. Step 1, let's get our constant out of the way. So plus 8, let's bring plus 8 to the other side by subtracting 8 on both sides. Okay, this is ax squared plus bx plus c. And what we want to do is add b over 2 squared to both sides. So if this is ax squared plus bx plus c, what is b? B is 10. Okay, so we're going to add b over 2 squared, 10 over 2 squared to both sides. Well, 10 over 2 squared, but we're not adding it to just one side, we're adding it to both sides. If we add it to both sides, we don't change anything. Okay, well, we can simplify this. 10 over 2 is 5. 5 squared is 25. Negative 8 plus 25 is positive 17. And also, this factors very nicely. We went from something that could not be factored as it was written to something that could be factored with just a constant on the other side instead of 0. So x squared plus 10x plus 25 is x plus 5 squared. Negative 8 plus 25 is 17. And now from here, square root property, pick up a plus and minus, and just subtract 5 on both sides. And you can leave your answer like that. That's completing the square. So it's kind of a weird method, kind of like a why are we doing this type of method? There are other ways. And honestly, you probably won't go for completing the square in most cases. And that's okay. There's a reason why we have a whole bunch of different methods to solving these things. So even if you don't use completing the square, that's fine. The other methods work just as nicely. 3x squared minus 6x minus 15 equals 0. Let's complete the square on this. However, we can only complete the square when a is 1. Well, ax squared, a is now 3. So just like that, we can't do completing the square, right? Just move on? No. What we can do is simply divide everything by 3, divide both sides by 3. Well, when we do that, 3x squared divided by 3 is just x squared. Negative 6x divided by 3, negative 2x, minus 15 divided by 3, negative 5. And it's nice because 0 divided by 3 is just 0. So this equation simplifies a little bit more nicely to x squared minus 2x minus 5 equals 0. Okay, now Let's complete the square. Let's get our constant term away. Let's add 5 to both sides. Now we want to add b over 2 squared to both sides. B is always the number attached to x. So b is -2. We're going to add b over 2 squared to both sides, -2 over 2 squared to both sides. -2 divided by 2 is -1. -1 squared is +1. Left side factors to x minus 1 squared. Right side simplifies to 6. And now square root property, take the square root of both sides, get plus and minus. X minus 1 equals plus or minus square root of 6, and add 1 to both sides. Okay, so completing the square, like I said, probably not something you do all that frequently, but quadratic formula is something you will definitely use at some point. So we need completing the square to derive the formula for quadratic formula. So I'm going to do it in the presentation. It's a little complicated, so if it scares you a little bit, don't worry too much. In general, you will never be asked to derive the quadratic formula, but I will still show it. If it freaks you out, skip along just a little bit. So in general, quadratic formula is the most powerful way to solve quadratic equations. I say that because it always works. It might be more work than necessary, but it always works. So if you're really struggling to try and factor, you're really struggling to try and use like square root property or completing the square, you can go right for quadratic formula, assuming that we're in the correct state for it. But yeah, it always works. It might be too much, but it's better to do too much than not enough. So to do this, the right side must be equal to 0. So factoring method, one side has to be equal to 0. Quadratic formula must be equal to 0 on one side, but completing the square root property, that is not the case. But okay, it's a little complicated to derive, like I said, but the quadratic formula is right here. For ax squared plus bx plus c equals 0, the solutions to ax squared plus bx plus c equals 0 is right here. X equals -b plus or minus the square root of b squared minus 4ac all over 2a, where a, b, and c all come from ax squared plus bx plus c. So if you know what a, b, and c are, you can go right for plugging in a, b, and c, and that's how quadratic formula works. I understand it's a very scary looking formula, but don't worry, it functions just like any other thing that you're plugging stuff into. Okay, so I am going to derive it for the presentation, for the sake of the presentation. However, if it's kind of scaring you or you're not really following along, don't worry, I'm just doing it for completeness. Skip ahead like, I don't know, 30 seconds to the first example, to skip over this part. But if you're sticking around, let's do it together. So we're going to complete the square. So let's bring positive c to the other side. So let's subtract c on both sides. And now we want to divide everything by a because we know we can only do completing the square when a is equal to 1. So we divide everything by a cancels out, b over a, and c over a. Okay, well now we want to complete the square. So we're going to add b, in this case, b over a divided by 2 squared to both sides. Okay, well, b over a divided by 2 is b over 2a. And we're going to add that to both sides. Yeah, it's already pretty messy. Now, left side is very nice. That factors to just x plus b over 2a squared. And now here, let's rearrange terms. Let's put b squared over 4a squared minus c over a. So I distributed the 2. I squared everything. B squared, 2 squared is 4. A squared is a squared. And just rearrange terms so that the minus would be to the right. Okay, well, what we can do is now combine these two terms by getting a least common denominator. So we need to multiply c over a by 4a so that we get a times 4a squared. Okay. Well, now they have the same denominator, so we can subtract them. Oh, b squared minus 4ac. That looks familiar. Well, now square root property says take the square root of both sides. When we do that, the square root cancels out. X plus b over 2a. This was a little bit of a mistake. This square root should still extend over everything. That was a small mistake. It should be square root of 4a squared at the bottom here. Okay, yeah. But now we can subtract b over 2a on both sides. Again, square root of 4a squared. It was still supposed to be square root here. Square root of 4a squared is 2a. Okay, well, now they have the same denominator, so we can add or subtract them. That was a very messy derivation. I promise it looks better in person. But yeah, if you wanted to know where it came from, there you go. So with that said, let's get right into examples. 3x squared equals 5x plus 2. So again, for us to do quadratic formula, we need everything to be on one side. So let's subtract 5x and let's subtract 2 on both sides. So one thing I should note is that you should always try and factor. If you're very good at factoring, if you're very comfortable factoring, you should try and factor first, because quadratic formula has a lot of space for you to make a mistake. So I believe this factors, yes, this factors, you would get two very nice rational answers. So in the event that you can factor, you should. But again, quadratic formula will always work, even if your answers are a little ugly. So for us to do quadratic formula, we need a, b, and c. Well, a, x squared plus bx plus c. So a is 3, b is -5, and c is -2. I'll do that again. ax squared plus bx plus c. Ax squared, a is 3, plus bx, b is -5, plus c, c is -2. And now what we're going to do is take a, b, and c and plug them in for a, b, and c. So we get that, right? Wherever we see a, write 3. Wherever we see b, write -5. Wherever we see c, write -2. Nobody said it was pretty, but at least now it's just calculation. Okay, -5 is +5. -5 squared is +25. -4 times 3 times -2, +24. 2 times 3 is 6. 25 plus 24 is 49. The square root of 49 is 7. So we get 5 plus 7 over 6, 5 minus 7 over 6. Well, it's a linear calculation, but not a very scary one. So our answers are -1/3 and 2. It seems very anticlimactic that quadratic formula ends up being just a calculation, but that's really all it is. There's some progression to get up to quadratic formula. If I just showed you quadratic formula, it wouldn't be very exciting, but at least now you understand where it comes from. Okay, let's do another one. 6x squared minus x minus 2. I think this is another one that could factor, but again, let's practice doing quadratic formula. Okay, well, this is already ax squared plus bx plus c. Again, ax squared plus bx plus c. Ax squared, a is 6, plus bx, b is -1, plus c, c is -2. So there's quadratic formula. Plug in a, b, and c and use parentheses so that you don't screw yourself up. Okay, -1 is +1, -1 squared is +1, -4 times 6 times -2 is +48. 2 times 6 is 12. 1 plus 48 is 49. Square root of 49 is 7. And again, 1 plus 7 over 12, 1 minus 7 over 12. We get 2 answers. So kind of not a mistake, but a coincidence that we have square root of 49 twice. That doesn't normally happen for every example. It just happens to work out for this one. Okay, and let's do another one. 5x squared plus 12x plus 4. So if this is ax squared plus bx plus c, a would be 5, b would be 12, and c would be 4. Alrighty, again, just plugging everything in. 12 squared is 144. 4 times 5 times 4 is 80. 144 minus 80 is 64. Square root of 64 is 8. Negative 12 plus or minus 8 becomes negative 12 plus 8 over 10, and negative 12 minus 8 over 10. And we again get two solutions. So you think that quadratic formula is this big, very ugly, very forgettable thing, but it's actually not that bad. If you know what A, B, and C are, if you plug them in correctly, it just becomes easy multiplication, subtraction, square roots. So don't be so scared of it. I understand it's daunting. It looks very scary, but it really is just a plug and chug. Okay, x squared minus 7x plus 7. Ax squared plus bx plus 7. A would be 1, b is negative 7, and c is positive 7. So plug it in. Negative 7 squared is 49. 4 times 1 times 7 is 28. Well, negative 7 is positive 7, but 49 minus 28 is just 21. And square root of 21 is not a pretty number. So going back to those square root property examples where I just said, leave it the way it is, don't worry too much about it. There you go. There's a perfect example of how this would look in quadratic formula. So instead of trying to figure out what square root of 21 is, instead of getting decimals, this answer, very nice and pretty. However, some instructors, if you're watching, you might prefer to have 7 plus square root of 21 over 2, comma 7 minus square root of 21 over 2. So this is a nice condensed form to say both solutions, but it would be a little bit more correct to write them out separately. However, less writing, the better. 2x squared plus 12x minus 18. You could do quadratic formula on this. However, what you might see is that all of these numbers are divisible by 2. So instead of dealing with a is 2, b is 12, and c is negative 18, why not just divide everything by 2? Well, when you divide everything by 2, you get x squared plus 6x minus 9. A, b, and c are not as big, and they will save you some time in simplifying. Again, you would get the exact same answer using 2, 12, and negative 18. It just might be a less simplified version. Okay, so again, plug it in. A is 1, b is 6, c is negative 9. 6 squared is 36. Negative 4 times 1 times negative 9 is positive 36. 36 plus 36 is 72, but square root of 72 is 6 square root of 2. So even though you don't get a perfect square on the inside, doesn't mean it's not simplifiable. I think that's a word. So square root of 72 is 6 square root of 2. Just because square root of 21 in the previous question was not able to be simplified, that doesn't mean all plain square roots can't be simplified. Okay, last but not least from here, let's just divide both of these by 2. Negative 6 divided by 2 is negative 3. 6 divided by 2 is positive 3. So this would be a nice, pretty final answer. If you got to this point, this is most of the work. You did most of the work right, but we're able to simplify just a little bit more. X squared minus 6x plus 9 equals 0. A is 1, B is negative 6, and C is 9. Okay, plug it in. Negative 6 squared is positive 36. Negative 4 times 1 times 9 is negative 36. Alrighty, 36 minus 36 is 0. And square root of 0 is just 0. Well, if you did 6 plus 0 divided by 2 and 6 minus 0 divided by 2, you would get 3 both times. So again, we've seen plenty of times that quadratic equations can give one solution or two solutions. Just because you get one type of solution over another doesn't necessarily mean you did anything wrong. However, just wanted to show you that we could have done this easier. You might have noticed it right away, but you could have also been very much in the quadratic formula groove. This can be factored as x minus 3, and you could get x equals 3 that way. So again, I just wanted to illustrate the fact that just because quadratic formula works every single time, it doesn't mean it is the easiest method. So just keep an eye out for when you want to use which method and try and use the best method for all of these problems. Well, what you notice a couple times is that we got things like two solutions, two rational solutions, or we got one solution like the last problem, or like that square root of 21 question where we had two solutions, but we knew square root of 21 was irrational, so we would end up being irrational anyway. So with that said, how do we know, how can we get foresight as to what type of answer we can get? Well, that's where discriminants come in. So the discriminant is the b squared minus 4ac in the quadratic formula. So we had negative b plus or minus square root of b squared minus 4ac over 2a. That b squared minus 4ac inside the square root is called the discriminant. Now, the discriminant is very useful because depending on the value of the discriminant, the quadratic formula produces different types of answers, different types of solutions. So if you know what the discriminant is, you can figure out which type of solutions you would get. Okay, if the discriminant is a perfect square, like those first two examples where the discriminant was 49, if it's a perfect square, there are two real rational solutions. Go back to those first two examples when we had square root of 49 and see that we had two very nice, very pretty fraction answers. They're real numbers and they're rational solutions. If the discriminant is positive but not a perfect square, like 21, there are still two solutions because we still had plus and minus square root of 21, but instead of being rational solutions, they're irrational solutions. So perfect square, two real rational, positive but not a perfect square, two real irrational. If the discriminant is 0, well, that was like that very last example we did where we only got x equals 3. So if the discriminant is 0, square root of 0 is 0, plus and minus 0 just goes away. You get one real rational solution. Last but not least, it didn't happen this time, but if the discriminant is negative, then you would get square root of some negative number, and there are two complex solutions. Now, we've spoken very, very little about complex numbers. I mentioned it all the way in P1. We kind of looked at it a little bit in P6 with square roots and saying, well, square root of a negative number doesn't exist. So in that case, we say there are two complex solutions, and it's almost like the entire next section is about complex solutions. So before we get into something like that, let's just do some very quick discriminant examples. 2x squared minus 3x minus 7. A is 2, B is negative 3, C is negative 7. Again, don't worry about solving it. Let's just determine what kind of solutions we would get without going through all the work. B squared minus 4ac, plug in A, B, and C, we get 9 plus 56, 9 minus negative 56, 9 plus 56 would be 65. 65 is positive, but not a perfect square, so we get two irrational solutions, two real irrational solutions, but we don't really know the difference between real and complex at this moment right now. Next section we will. X squared plus 6x plus 9. A is 1, B is 6, C is 9. So plug that all into the discriminant. 6 squared is 36. 4 times 1 times 9 is 36. 36 minus 36 is 0. We got 0. That is one rational solution. X squared plus 2x plus 3 equals 0. All right, A is 1, B is 2, c is 3. Plug it in. 2 squared is 4. 4 times 1 times 3 is 12. 4 minus 12 is negative 8. That's negative 2 complex solutions. And we will talk about 2 complex solutions in 1.4. So I will see you there. Bye. Hi, everyone. Welcome back to section 1.4. At the end of 1.3, we very briefly talked about the fact that the discriminant can be negative in quadratic formula. Well, that's kind of an issue because the discriminant usually sits inside a square root. So we're saying that we can take square roots of negative numbers, which to this point, we have not been able to do. However, what we are going to introduce in this section is the complex numbers. So before I do that, I just want to very briefly discuss what the complex numbers are. All the way in P1, we talked about the set the natural numbers, which were the counting numbers 0, 1, 2, 3. And we said the natural numbers sit inside the set the whole numbers, and the whole numbers sat inside the set the integers. The integers sat inside the rational numbers. And then we had this weird little set on the outside, the irrational numbers, and both the rational and irrational numbers made up the real numbers. So the real numbers are any numbers that, even if not pretty, even if not easily calculable, do sit on the real number line. For example, you may not necessarily know where exactly, negative 1.12479 sits, but you have an idea and you can picture where it sits. However, what we're going to introduce today is the complex numbers. So the complex numbers are this set that includes all of the real numbers, and we denote it with a capital C. And what we're going to add in this set are what are called imaginary numbers, where we are now allowed to take square roots of negative numbers. Even if we cannot necessarily visualize what the square root of a negative number is, it does have very many properties, both in this course and in all of mathematics and in the real world. So just wanted to give this brief visual, and now we're going to move back to the presentation. Okay, so now we're back in the presentation. Now you see the name of the section, the complex numbers. So let's get right into it. So like we said, the natural numbers go inside the whole numbers go inside the integers go inside the rational numbers. Along with the irrational numbers, the rational numbers go inside the real numbers. And now this real numbers set goes inside what we call C, the complex numbers. Now, the complex numbers introduce the unit I, where we say and where we define I to be square root of negative 1, but not specifically just square root of negative 1. We have the added property that I squared equals negative 1. So normally we have these rules that when we square root, we're supposed to get positive numbers and all that. But in the set of the complex numbers, this is a rule that is allowed to happen. So again, just because we have I equals square root of negative 1 doesn't necessarily mean that all of our numbers are going to have I or are going to be imaginary. The real numbers sit inside the complex numbers. So just like all natural numbers are whole numbers, just like all whole numbers are integers, all real numbers are complex numbers. So even if it doesn't have an I, it is still a complex number. So we use the notation Z equals A plus BI. Z is what we use to denote complex numbers in general. Instead of a C, right, we like using C for constant. So Z will denote complex numbers. So we have A plus BI. That is what a complex number would look like. A and B themselves, ignoring I for a second, A and B are just both real numbers, numbers that we have dealt with before. We say A is the real part, and we say B, the part that is attached to the imaginary unit I, is the imaginary part. So the part that is attached to square root of negative 1 is the imaginary part. We can visualize the real part. This could be like 2, and you know where 2 sits, but you might not necessarily know where 2 plus 3i sits. We can also call it the complex part, imaginary part. We get the idea. Now, if A equals 0, well, then we have 0 plus BI, which is just BI, and a number that only has an imaginary part we say is purely imaginary. And if b equals 0, so a plus 0i, well, 0 times anything is still 0, even in the complex numbers. And that would give us just a, which itself is a real number. So one kind of added property, but goes along with what we're talking about, that if we have some b that is positive, so square root of negative b, where this isn't positive, this is a negative number. Okay, square root of negative b, we separate this by saying square root of negative 1 times square root of b, right? Breaking up the product. And then square root of negative 1 is just I. So we say this is I square root of b. Okay, now I want to stress that this breaks the rule of radicals that we talked about all the way in P6. In P6, we said we can only separate roots if the insides are both 0 or positive. But in the complex number system, we are allowed to separate them. That is a rule of the complex numbers. Now, that's kind of unfamiliar to many of you if you have not seen imaginary numbers before, but essentially there are more than just the real number system out there. The most common number system, the one that we're most familiar with, is the real numbers. All numbers that we can add, subtract, visualize, graph, stuff like that, but there do exist other number systems that have their own sets of rules. Complex numbers is the beginner of sets that break apart from the real numbers. But if you go higher up in math, you can find all sorts of very, very crazy number systems. So I just want to stress that the complex numbers are their own set, are their own system, just like the natural numbers, just like the whole numbers, and so on. Okay, so just to get an idea on what real parts and imaginary parts look like, 2 plus 5i, well, this is a plus bi. The real part is the part that sits by itself, and the imaginary part is the part that is attached to I. So the real part here would be 2, and the imaginary part would be 5. Okay, pretty straightforward. 7 minus 1/2 I. The real part is the part that doesn't have I, which is 7. The imaginary part isn't just 1/2, it would be negative 1/2. Okay, that makes sense, the negative sign. 3i, well, 3i is completely missing a real part, right? It only has the I part. Well, we can rewrite this as 0 plus 3i. Well, now it's a little clear that the real part is 0 and the imaginary part is 3. Negative 9, completely missing the I part, but we can rewrite negative 9 as negative 9 plus 0i. Okay, well, the real part is negative 9. The imaginary part is 0. So if the imaginary part is 0, we would say it's just a real number. Negative 9 is a real number. We know that. And for the case of 3i, where the real part is 0, we would say that's a purely imaginary number. 3 plus square root of negative 25. Well, we have to simplify square root of negative 25 first. In general, always simplify square roots of negative numbers before you do anything else. Well, the square root of negative 25 would be the square root of 1 times the square root of 25. Square root of negative 1 is I, and square root of 25 is 5. Another way you can look at this is the square root of positive 25 is 5. So the square root of negative 25 is 5i. And you can extend that to all square roots of negative numbers. Square root of 64 is 8. Square root of negative 64 would be 8i. The real part, now that we have it rewritten, is 3, and the imaginary part is 5. Okay. Now, what we're interested in doing, of course, is all sorts of operations. All these operations will eventually get us back to quadratic equations, just like we finished 1.3 with. Okay, so some operations, addition and subtraction, they are a lot like combining like terms for polynomials. So if we are adding or subtracting complex numbers, we are going to add and subtract their real parts, add and subtract their imaginary parts. So kind of thinking about this as combining like terms, you add all the constants together, you add all the x's together, all the x squareds, and so on. So 2 plus 3i plus 1 plus 4i, we are going to add 2 and 1, and then separately add 3i and 4i. Well, 2 plus 1 is 3, 3i plus 4i is 7i. If you want to substitute x in for I, just so it's a little bit easier to look at, that's totally fine too. 3 plus 7i plus 2 minus 4i. We're going to add the real parts, 3 and 2, and then add 7 and negative 4i, or just subtract 7i and 4i. 3 plus 2 is 5. 7i minus 4i is 3i. 5 plus 9i minus 6 minus 8i. Let's be a little careful. We're going to subtract the real parts, so 5 minus 6 and 9i minus negative 8i for the imaginary parts. 5 minus 6, negative 1. Negative negative is a plus, 17i. If we have square roots, like I said, simplify the square roots. First, square root of negative 9 would be square root of negative 1 times square root of 9. Square root of negative 4 would be square root of negative 1 times square root of 4. Okay, well, square root of 9 is 3. Square root of negative 9 is 3i. Square root of 4 is 2. Square root of negative 4 is 2i. And now, just subtracting real and imaginary parts. Okay, so not so bad so far. And multiplication isn't that much different, except think about this. If you have been thinking about I as x, well, when we are doing, for example, foiling and we get x squared, well, x squared just stays x squared. It's its own thing. But if you're doing it with I, we have the rule that I squared equals something specific. So it's just one extra step of simplification. So we say in the complex numbers that I squared is negative 1. So when doing multiplications with square roots, with imaginary parts, write the square roots as that I square root of b form before, and do that before multiplying. Okay, 3 minus 5i times 2 plus 7i. Let's treat this just like foiling. So we're going to do 3 times 2 is 6. 3 times 7i is 21i. Negative 5i times 2, negative 10i. Negative 5i times 7i, negative 35i squared. Let's simplify this inside right here. 21i minus 10i would be 11i. And now, if this was polynomials with x's, we would be done. However, in the complex numbers, when we're talking about I, we have one added step, that I squared equals negative 1. Okay, negative 35 times negative 1 is positive 35. So our extra steps just lead us to adding real parts. 6 plus 35 is 41. Now we like writing 41 plus 11i. We like writing the I term second. That's just how we decide to write them. If you wrote 11i plus 41, you're not necessarily wrong. It's just a little bit nicer to put the imaginary part second. 2 plus 5i times 1 plus 4i. Okay, 2 times 1 is 2. 2 times 4i is 8i. 5i times 1 is 5i. 5i times 4i is 20i squared. 8i plus 5i is 13i. 20i squared, well, I squared is negative 1. So 20 times negative 1 is negative 20. 2 minus 20 is negative 18. So again, we kind of like writing that minus second, 13i minus 18. It is more correct to put the imaginary part second. So it's kind of interesting because all of these terms here are positive. And in polynomials, everything positive that we're multiplying, we end up with everything positive at the end. But we see in the complex numbers, we get this weird behavior that sometimes we can still get negative numbers. Negative 2i times 5 minus 9i. This is just distribution. Negative 2i times 5, negative 10i. Negative 2i times negative 9i, positive 18i squared. I squared is negative 1. So 18 times negative 1 is negative 18. Okay. 3i times 7 plus 4i. 3i times 7 is 21i. 3i times 4i squared, 12i. 3i times 4i is 12i squared. I squared is negative 1. So we get negative 12 plus 21i. So just be careful. Treat these problems as their own separate problems. In the event that you have square roots, simplify the square roots first. So square root of negative 2 is square root of -1 times square root of 2, essentially pulling out that -1 in terms of a square root. Square root of -8 is square root of -1 times square root of 8. Square root of -1 is I. Square root of -1 is also again I. So I times I is I squared. Inside the square roots, 2 times 8 is 16. Well, I squared is -1. Square root of 16 is 4. So our final answer is -4. And again, be very careful. This is true for the complex numbers. What we would do in the real numbers, but we wouldn't actually do it in the real numbers because we're not allowed to have square roots, negatives inside square roots to begin with in the real numbers. This is only allowed in the complex numbers. But just be careful. Make sure you simplify this with I first, because if you go right for combining the insides, you would get -2 times -8 is +16, and square root of +16 would be 4. So please be very careful. The rules of complex numbers dictate that we need to take out I first when we are dealing with square roots of negative numbers. Okay, and there's actually a really interesting property surrounding I and the powers of I. So we know that I to the 1 is just I. We know that I squared is -1. Well, then I cubed would be I squared times I, but I squared is -1. And -1 times I would be -I. Okay, but I to the 4th, well, I to the 4th is I squared times I squared. I squared is -1. I squared is also -1. And -1 times -1 is +1. Oh, that is weird. Okay. Well, I to the 5th would be I to the 4th times I, right? Just using properties of powers. I to the 4th is 1, and I is just I, so 1 times I is just I. Okay. I to the 6th, I to the 4th times I squared. I to the 4th is 1, and I squared is -1. Well, 1 times -1 is -1. I to the 7th is I to the 4th times I cubed. I to the 4th is 1, and I cubed is -I. So 1 times -I is just -I. Oh, well, hold on. I, -1, -I, 1. I, -1, -I. Maybe there's already a pattern. Okay, I to the 8th would be I to the 4th times I to the 4th, but I to the 4th is just 1, and 1 times 1 is 1. Look at that. The powers of I cycle. I, -1, I, 1. I, -1, I, 1. So what do you think is going to happen for I to the 9th? Well, I to the 8th was 1, so we cycle again back to I. I to the 10th would be the next one in the cycle, -1. And then -I. And then 1. I to the 13th, wow, look, the cycle is exactly the same. I, -1, I, and 1. Very, very strange. Okay, now, before we get into actually solving quadratic equations using complex numbers, we got to talk about division a little bit. And division is kind of weird. Okay, so complex division is a lot like rationalization. Go all the way back to P6 when we talked about rationalizing denominators, and that's going to be very, very, very similar to here. Okay, so what we're going to do is multiply by the conjugate. So the conjugate of A plus BI would be A minus BI, and vice versa. Think back to the conjugate of A plus B. Conjugate of A plus B is A minus B, and the conjugate of A minus B is A plus B. So phraseology is the same. Conjugate, its application is still the same, where if we have A plus BI, its conjugate is A minus BI. If we have A minus BI, its conjugate is A plus BI. So now the complex conjugate product theorem, very long mouthful, the complex conjugate product theorem says when we multiply these things, when we multiply something by its conjugate, well, A times A is A squared, BI times -BI is -B squared I squared. Notice we don't have to do the inside. That's just foiling. but this is also just difference of squares, right? A plus something, A minus something, difference of squares. Well, I squared is -1. So negative b squared times -1 would be positive b squared. Oh, that's really weird. Okay, so if we are multiplying something by its conjugate, if we're multiplying a complex number by its conjugate, all we need to do is take the real part and square it, and then add the imaginary part squared. Forget about the i's. No more i's here. So if you don't like what I just did, that's okay. You are more than welcome to FOIL, but this is going to save us a lot of time. So let's do z by z bar. That's what this little z with the bar on top, literally z bar. Okay, so if we're multiplying 2 plus 5i by its conjugate, we're multiplying by 2 minus 5i. Well, if you want to FOIL this, you can, but the complex conjugate product theorem says 2 times 2, take the real parts, square them, plus take the imaginary parts and square them. Take 2, square it, plus take 5 and square it. 2 squared is 4, 5 squared is 25, and you get 29. So again, if you want to FOIL, you can, but you don't have to. Okay. 7 minus 1/2 I, if we want to multiply by its conjugate, the conjugate of 7 minus 1/2 I would be 7 plus 1/2 I. And here is a great example of why you wouldn't want to expand this. Well, here what we're going to do is take the real parts, square them, plus take the imaginary parts and square them. 7 squared plus 1/2 squared. 7 squared is 49. 1/2 squared is 1/4. And properties of fractions, that's chapter P. 3i, well, 3i here is a little bit of a problem. There's no real part, but fear not. 3i is just 0 plus 3i. Okay, well, 0 plus 3i, its conjugate is 0 minus 3i. So take the real parts, square them, take the imaginary parts, and square them. 0 squared plus 3 squared. And we just get 9. Okay, now we did it this way so that it's a lot easier to do division. Okay, so what we're going to do for complex division is multiply by the conjugate, exactly like we rationalized the denominator. We don't want I in the denominator here. All of the complex numbers we've talked about so far have all been in the numerator. Okay, so the conjugate of 2 plus I would be 2 minus I. And just like everything else we've done, multiply it in the numerator and in the denominator. So what we get is 1 times 2i over 2 plus I times 2 minus I. Oh, look at this. Complex conjugate product theorem says take the real part 2, square it. Take the imaginary part, there's a 1 right here, and square it, add them together. 1 times 2 minus I is just 2 minus I. Real part squared plus imaginary part squared. 2 squared is 4. 1 squared is 1. 4 plus 1 is 5. Now, I like this answer. This is pretty clear. However, it is very mathematically sound to say 2/5 minus 1/5 I, just so it's a lot clearer that this is the real part and this is the imaginary part. So again, I would accept this, but those of you watching elsewhere, be careful. This might be better for your instructors. Okay. And again, if you don't like what I did, that's totally fine. You still have to multiply by 2 minus I over 2 minus I, but when it comes to the denominator, if you feel better foiling this, that's totally okay. 2 times 2 is 4. 2 times negative 2i is negative 2i. I times 2 is positive 2i. I times negative I is negative I squared. Well, we can simplify that inside. Negative 2i plus 2i goes away. I squared itself is negative 1. So 4 minus negative 1 would be 4 plus 1, and that's 5. And just like that, we get to the exact same answer. Okay, some more examples. 1 plus I over 1 minus I. We're going to multiply by the conjugate of the denominator, always. Conjugate of 1 minus I is 1 plus I. Okay, so in the numerator, we get 1 plus I times 1 plus I. We're going to need to FOIL that. But in the denominator, 1 plus I, 1 minus I, complex conjugate product theorem. Take the real part 1, square it. Take the imaginary part 1, square it, and add them together. Up here, 1 times 1 is 1. 1 times I is I times 1 is I, so we get 2 i's. I times I is I squared. Okay, well, 1 squared is 1. 1 squared is 1, so we get 2. And I squared is negative 1. 1 minus 1 goes away. So 1 plus I over 1 minus I is just I. Ooh. There is very little rhyme or reason. You should be trying to do all these problems on their own. Don't look for patterns like this. This is just a nice example that happened to work out. Okay, 7 plus 6i over 3 minus 4i, multiply by the conjugate of the denominator. Conjugate of 3 minus 4i is 3 plus 4i. In the numerator, FOIL this out. In the denominator, take the real parts, square them, plus take the imaginary parts and square them. So I FOILed at the top. At the bottom, 3 squared plus 4 squared. Okay, 28i plus 18i, 46i. 3 squared plus 4 squared is going to be 9 plus 16. I squared is negative 1. 24 times negative 1, negative 24. Alrighty. Nobody said these were going to be pretty. But now we get the idea. Okay, now that we have learned to sort of work with I, what we can now do is actually solve quadratic equations where we get 2 complex solutions. Okay, so when the discriminant is less than 0, our final answer is a pair of complex roots. Don't forget from the discriminants part in the last section that if the discriminant is negative, what type of solutions we get is 2 complex solutions. So x squared plus 2x plus 2 equals 0. Okay, well, A is 1, B is 2, C is 2, just like we did in the last section. But now let's plug in all of that information to the quadratic formula. All right, well, 2 squared is 4. 4 times 1 times 2 is 8. 4 minus 8 is negative 4. Okay, well, the square root of positive 4 is 2, so the square root of negative 4 is 2i, and now we can divide everything by 2 to get negative 1 plus or minus I. Okay. X squared minus 4x plus 13 equals 0. A is 1, B is negative 4, C is 13, right? Just to reiterate, ax squared plus bx plus c. Alrighty, and just plug it into quadratic formula. Negative 4 squared is positive 16. Negative 4 times 13 is negative 52. 16 minus 52 is negative 36. Square root of positive 36 is 6. Square root of negative 36 is 6i. And we can divide both 4 and 6 by 2. Nice. One more. 4x squared plus 4x plus 5 equals 0. A is 4. B is 4. C is 5. Plug it all in. 4 squared is 16. 4 times 4 times 5 is 80. 16 minus 80 is negative 64. The square root of negative 64 will be 8i. We can divide all of these things by 4. And just like that, that's the end of 1.4. So most of the section, even though our goal was to solve quadratic equations that involved I, what we ended up doing is spending more time just doing complex number acrobatics. So yeah, that's the end of 1.4. And 1.5, we're going to extend what we did in 1.1 and 1.3 to solve equations that have almost any power and a whole bunch of other weird looking things. So I will see you in 1.45. In 1.5. Bye. Hi, everyone. Welcome back for 1.5. In 1.1, we solved linear equations, and in 1.3, we solved quadratic equations. And we're just going to talk about almost every other type of equation that we could possibly solve at this level. So a lot of it's going to use things like solving linear equations, things like splitting apart multiple linear equation factors into multiple answers. But in general, we're going to be talking about quite a few different types. So in a way, 1.5 is kind of like a showcase. You already see all the different types of things that we're going to learn to solve here, like factoring, rationals, radicals, rational exponents, and quadratic likes. So there's a lot going on here. Take each subsection as kind of its own, actual subsection, but how we solve each one is very different. But again, what we're going to use is a lot of what we have talked about in 1.1 and in 1.3. One thing I want to stress before we do any of these is that, in 1.1 and in 1.3, I said, make sure you check your answers. And in 1.1 and 1.3, linear and quadratics, you don't really have that problem, really. Whatever answer we get is going to be the right answer. But what you're going to see here in 1.5 is that it is possible for us to get what are called extraneous solutions. Solutions that we get when we apply a certain algebraic method, but when you go back to plug them in, they don't actually work. So you're going to see me check a lot of answers here and say like, oh, look, this answer doesn't work. So just in general, I've been saying it for a while here in chapter 1, but please check your answers when you are doing these types of problems. So let's get into the first type. Let's talk about factoring. And we've kind of been doing this. We've factored quadratics before. Well, all we're going to say here is if we can factor the thing, we can solve it just like we've solved anything else. So again, if we can factor it, we can solve it. So let's say we have x cubed plus 3x squared equals 4x plus 12. And what we're going to do here to solve this, let's bring everything to one side. So let's subtract 4x on both sides. Let's subtract 12 on both sides. Okay, and now what we have are 4 terms whose collective greatest common factor is 1. That was usually a really good heads up for us to do factoring by grouping. So let's factor the first 2. Let's factor the second 2. We see here in the first 2, we could take out an x squared. In the second pair, we could take out a negative 4. Oh, well, they have x plus 3 in common. We can factor out x plus 3. And then everything that's left over, right? P4, us factoring. Well, we also know that x squared minus 4 is also x plus 2x minus 2. And now from here, this is actually pretty nice. What we had in 1.3 was 2 factors that were multiplied to 0, and we set each factor equal to 0. Well, we can extend this to however many factors we have multiplied equal to 0. We could set all of them equal to 0. And now from here, these are all just linear equations. Subtract 3 on both sides, subtract 2 on both sides, and add 2 on both sides. So we get 3 answers. Now, maybe there is some sort of pattern where the fact this is x cubed, we had 3 answers. Maybe x to the 4th would have 4 answers. And we're not going to really broach as to how or why that is the case until chapter 3. So, don't be looking necessarily for 3 answers if you only get 1 answer, right? There is a theorem to this, but we're not going to talk about that theorem for a while. But there we go. Really no different from quadratics. It was factor and set each factor equal to 0. And the only difference is the factoring was a little different, and we had 3 answers instead of 2. So factoring, just factor the thing, right? So x to the 4th equals 9x squared. Same thing. Let's get everything to one side. So let's subtract 9x squared on both sides. All right, well, these 2 things have x squared in common. So let's factor out x squared. Then x squared minus 9. We can make that x plus 3x minus 3, difference of squares. And now we again have 3 things that are multiplied to 0. So let's set each one equal to 0. Well, x squared equals 0. The only location where that is 0 is 0. X plus 3, let's subtract 3 on both sides. X minus 3, let's add 3 to both sides. And we again get 3 answers. So last one was x cubed. We had 3 answers. This one is x to the 4th. We have 3 answers. So
like I said, don't look for patterns right now. We'll talk about what that pattern is in quite a while, in several videos. We have an entire chapter 2 to get through. Okay, but what I want to make sure is that you don't do this. What you are very tempted to do is that you just divide both sides by x squared. Oh, right, we can divide numbers. We can divide x squareds. So you divide x squared on both sides, and x squared cancels out. X to the fourth over x squared is just x squared. And then you take the square root of both sides. You get plus and minus square root of 9, which would give us x equals plus and minus 3. But here's the problem. The answer we had in the previous slide had 3 answers. For the exact same problem, one of them was 0. But when you take the square root of both sides like we just did, you only got 2 answers. So there's a larger issue at play here, where if you divide by x squared, what you're essentially allowing is that you divide by 0, right? X equals 0 is an answer. Well, if x is 0, then you just divided by 0 squared. And at no point in this class, and no point in almost any class, will you ever really broach the topic of dividing by 0 in a meaningful way. We know that anything divided by 0 is undefined. So don't divide by variables, only divide by numbers. Okay, so again, factoring, always go for factoring. Do not try and divide by variables or x's. Okay, so factoring, there's really not a whole lot to say there, right? If you could factor it, you can do it. But let's get into all other different types of equations, things that we have worked with before, but maybe not necessarily have solved before. Okay, so let's do some rational equations. And rational equations, well, rational numbers are numbers that are fractions. Rational equations are just equations that are fractions. So we have 1 over 6 plus 1 over x plus 1 equals 1 over x. And what we're going to do, the method to solve rational equations is to multiply everything by the least common denominator. We spent a lot of time in P5 talking about least common denominators. You know how to do it with numbers, and we talked about how to do it with variable terms. So let's multiply everything by the least common denominator. In our case, let's look at all the denominators we have. 6, x plus 1, and x. Well, I know x plus 1 and x look a lot alike, but as factors, they don't have anything in common, right? If x is 2, then this is 2, and this is 3. So 2 and 3 don't have anything in common. So instead, multiply everything by the LCD. Our LCD would be 6 times x plus 1. And we're going to multiply it on both sides. Now, there's kind of an issue here that is very similar to that last issue I talked about in factoring, but what we're going to get is something a little different in what we did for factoring, that very last, don't do this example. What we got in that case is you lost answers, but maybe we get something a little different here. So let's distribute this least common denominator to each and every numerator, right? This is like an imaginary 6x, x plus 1 over 1, and then it just becomes fraction multiplication. 6x, x plus 1 times 1, 6x, x plus 1 times 1, 6x times x plus 1 times 1. And now what you probably see is that some things cancel out. How nice. 6 cancels out here. X plus 1, the whole factor cancels out here. And x, that cancels out here. Oh, that's really, really nice. Cool. All righty. From here, we can distribute x. We can distribute 6. We can combine x and 6x. If you have 1 apple and I give you 6 more, you now have 7 apples. Let's bring 6x plus 6 to the other side. Let's get everything to one side. So let's subtract 6x and 6 on both sides. Well, 6x minus 6x, that goes away. 6 minus 6, that goes away too. That's the whole point. But here, you have 7 apples, and then I take 6 more of them away. Now you're back to 1 apple, and now we're here. And wow, look at that. We have a nice, very pretty, factorable equation. So we factor x squared plus x minus 6 to x plus 3x minus 2. Again, go back to the P4 video if you want to see practice on how to factor. And now set each one equal to 0, and we get x equals negative 3 and x equals 2. So 2 answers. Okay, nothing weird happened in that question, but I already told you that something weird still might happen. Let's see. All right, 1 over x minus 1 over 5x plus 10 equals 1 over 5. Well, before we try and determine what the least common denominator is, I've been preaching factoring for so long. Let's factor this middle term. We can pull out a 5. Okay, well, now we're still going to multiply by the LCD, but notice that we don't need to multiply by 5 twice, right? This 5 is here, this 5 is here. Okay, we got to multiply by a 5 to everything, multiply by an x, multiply by an x plus 2. So you could have multiplied by x times 5x plus 10 times 5. Your numbers would be just a little bit bigger, maybe a little bit weirder to deal with toward the end. So again, factoring saved us from needing to multiply by an extra 5. Okay, well, put all this into the numerators. And now I didn't really stress it in the last example, but notice something. The reason we multiply everything by the LCD is so that we get rid of the fractions. In general, fractions, scary. We don't like dealing with fractions. So what is instead quite nice is by multiplying everything by the LCD, all the fractions go away. And that's the benefit to multiplying everything by the LCD. So here, x is going to cancel out. Here, x plus 2 and 5 is going to cancel out. And in the last one, 5 is going to cancel out. So again, the method of multiply everything by the LCD is very nice because it gets rid of all of the fractions. The less fractions we need to deal with, definitely the better. All right, let's distribute a 5. Let's distribute an x. 5x minus x is 4x. And let's bring everything to the right-hand side. So let's subtract 4x on both sides. Let's subtract 10 on both sides. 2x minus 4x, you have $2 and you spend $4. You are now $2 in debt. And this doesn't factor, but you know what? Why not? Let's do some more quadratic formula practice. A, if this is ax squared plus bx plus c, a is 1, b is -2, and c is -10. Quadratic formula looks like this bad guy right here. And let's plug in everything we know. B is -2, B is -2, A is 1, C is -10, and A is 1. Alrighty. -2 is +2. -2 squared is +4. -4 times 1 times -10 is +40. 4 plus 40 is 44. We can rewrite square root of 44 as square root of 4 times 11. Square root of 4 is 2. And now we can divide both of these by 2. We can, in a sense, distribute the parts of the numerator with the denominator. So 2 over 2 is 1. 2 squared 11 over 2 is 2 square root of 11 over 2. And, I wanted to do this just to make sure that you don't try and cancel out just one of these 2's. Don't forget, we can only cancel things out when everything is multiplied or divided. So, just very briefly going back to what we had here, we were able to cancel out x because it was 5 times x times the factor x plus 2. That's why we could factor out x. 5 times x plus 2. 5 times x plus 2. That's why things can cancel out. So there is a little bit of a reason why we are able to do these things. So again, don't just try and cancel out one of the 2's. You're dividing both of them by 2 because we got this plus and minus up here. Well, 2 divided by 2 is 1. 2 divided by 2 is also 1. And we're left with just square root of 11. Okay, so maybe still nothing weird. I might have misremembered when the weird things happen, but I swear they do happen. Maybe it happened. I think it happens in this one. So far, nothing really weird, right? We got answers that worked out nicely. You should be checking the answers on your own. I don't want to spend time just plugging in answers unless there's a problem to show you something new. So let's do it again here. All right, we're going to multiply everything by the LCD, but instead of trying to multiply everything by x minus 1 times x plus 3 times x squared plus 2x minus 3, well, it's really nice that we could factor and see that, oh, look at that. This has an x plus 3. This has an x plus 3. This has an x minus 1. This has an x minus 1. Multiply everything by x plus 3, x minus 1. Okay. All righty. Well, here again, let's distribute all of these to numerators. So x plus 3x minus 1 times 1, x plus 3 times x minus 1 times x this time, x plus 3x minus 1 times 4. And now you see things cancel out. X minus 1 goes away. X plus 3 goes away. X plus 3 and x minus 1 goes away. And now we're back to just a regular equation. If you multiply everything by the LCD and things don't cancel out, you might have done something wrong. You might have chose the wrong least common denominator. So either one, you don't do it right the first time and you accidentally make a mistake, or two, you didn't multiply by enough. And all you would need to do is just multiply by a little bit more. You can do it in 2 steps. That's fine. Just make sure that if you are multiplying and canceling things out, you're doing that part correctly. Okay, now that we're back to a regular equation, let's distribute this x. Then let's combine some like terms. X minus x. Oh, well, that just goes away. We can subtract 4 on both sides to get 0 on one side, right? We like having 0 on one side. X squared minus 1 factors to x plus 1, x minus 1, and we set each factor equal to 0, and I think we're pretty okay on that part. So we have 2 answers, right? Everything we've been doing so far, we've had 2 answers for rational equations. That is, to an extent, a coincidence for the types of rational equations we're looking at. But yeah, both are answers, right? We haven't had any problems so far. But very large BUT. Okay. Well, if you don't see it right away, let's go in and check our answers. Well, I'm going to let you check x minus 1 on your own, but let's check x equals 1 together. When we plug in x equals 1 back into our equation, we plug x equals 1 here, 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 and here. And what you see is 1 minus 1 and 1 minus 1. Well, 1 minus 1 is 0. 1 minus 1 is 0. 0 times anything is 0. So we have 2 of our 3 fractions that when we plug in x equals 1, we get something that is undefined. And that is not allowed. So going back to what I mentioned way back in the beginning of the section is that we sometimes get these things called extraneous solutions. That we've been doing this algebraic method of multiplying everything by the LCD. But when we did that, even though it worked 2 of the times, this 3rd time that we did it, we got answers that didn't work out nicely. Or not, I wouldn't say didn't work out nicely, but they caused problems. They're not in the original equation's domain. We've kind of brushed domain so far. We're going to talk more about domain in 2.4, but look at the original denominators. You were never allowed to have 1 here. You were never allowed to have -3 here. So make sure when you check your answers that you don't run into problems like this, where 1 over 0 is literally undefined. 4 over 0 is undefined. X was never able to be equal to 1. X was never able to be equal to 1 to begin with. So x equals 1 is extraneous. It doesn't count. The only solution is x equals -1. So for the first time here in chapter 1, it is justified that I say check your answers. You should be checking your answers for everything just to see if you get answers that make sense. Or just to make sure your answers are right, I should say. But, we run into very bigger problems sometimes, especially here in 1.5. So even though we got 2 solutions algebraically, only one of them is true when you go back to plug it in. Okay, let's do another one like that. X over x minus 1 minus 1 over x plus 1 equals 2x over x squared minus 1. All right, rhyme and reason. Let's factor, and you see the least common denominator is just the combination x plus 1, x minus 1. Everything that we would need to cancel out every denominator. All right, let's distribute x plus 1, x minus 1 to each numerator. And now what you see is a bunch of things cancel out. X minus 1 goes away. x plus 1 goes away, x plus 1 and x minus 1 goes away. Now we're back to a normal equation. Let's distribute x. Let's distribute a negative 1. X minus x goes away. Let's subtract 2x on both sides. And now we get something that factors to x minus 1, set each one equal to 0. Oh, and we actually only get one solution this time. And that's just a quirk of what the question was. But it's possible. It's possible you get an answer that happens twice. There's nothing wrong with that. It just means there's only one answer, just like it happened in 1.3 sometimes. But okay, and maybe you see what's going to happen next. Let's check x equals 1. And we actually run into the exact same problem that we had before. When we plug in 1, 1 minus 1 is 0, and 1 squared minus 1 is also going to be 0. Oh, look at that. X equals 1 is extraneous. That's a problem. But one thing that's weird here is that in the last question, when we had an extraneous solution, we had two answers, and one of them was extraneous, so the other one was the answer. But here, we have x equals 1 is our only solution, and our only solution is extraneous. Well, that just means there's no solution. So if your only potential answer doesn't work, that's okay. It doesn't mean that like, oh, well, it's the only answer. It has to work. No, it's possible that there is no solution to the equation. And that's very much okay. So don't be afraid to say that all of your solutions are wrong. I mean, if all of your solutions are wrong because you got the wrong possible solutions, that's one thing. But it is entirely possible that there just is no solution to an equation. Okay, we carry on. So that was rational equations. And what we're going to talk about next are radical equations, or, totally radical equations. Don't laugh at that. That wasn't funny. But radical equations are, you guessed it, equations that have radical signs. That's it. Okay, here's what I want you to think about. When we are doing regular, polynomial equations, like quadratic equations, we talked about how if we have x squared equals a number, we can take the square root of both sides. Well, that means that x to the 2, the way we undo x to the 2 is to take the square root of both sides. Okay, well, if we have x cubed, the way to undo x cubed would be cube root of both sides. Well, how do you then undo square root or cube root or fourth root or fifth root? Well, you guessed it. The way we undo roots are by raising both sides to that power. That's it. All right, so all we need to do is raise both sides to the third power. Same way as square root cancels out x squared, kind of, right? There are some quirks there, but same way that cube root, the same way that square root cancels out squared is the exact same way that cubing both sides cancels out cubed. All right, well, so cube root and 3 go away. We're left with just the inside. 3 to the 3 is 27. And now we're just back to a linear equation. Subtract 6, divide by -3, and we get x equals -7. Nice. That's it. All right, well, what if we have cube root of -3x plus x equals -3? Well, is it a problem that we got a negative on one side? I don't know. Let's see what happens. Well, we cube both sides again. Inside is just -3x plus 6. Right side, we now get -27. And we subtract 6 again, and we divide by -3, and we get 11. Oh, there's nothing wrong with there. Don't forget, way back in P6, we said cube roots, odd roots, can produce negative numbers, right? Cube root of -27 is -3. The problem arose when we were doing even roots. For example, square roots were never equal to negative numbers. fourth roots were never equal to negative numbers. So it is a little different depending on the root. If your root is odd, it's okay that you have negative numbers on one side. There's nothing wrong with that. But maybe something is weird when we have even roots. Let's think about that. All right, so we have fourth root this time. Does that mean we completely change how we solve this problem? No. So last one, we had cube root. We raised both sides to the fourth power. Guess what? We're just going to, last question was cube root. We raised both sides to the third power. This one's fourth root. We're just going to raise both sides to the fourth power. Again, fourth root and to the fourth cancel each other out. Negative 3x plus 6 equals 3 to the fourth, which is 81. Subtract 6 on both sides. Divide negative 3, and you get negative 25. Absolutely nothing wrong there. Well, let's try and do the exact same thing, but with fourth root of negative 3x plus 6 equals negative 3. And you notice that the slide doesn't have as much info on it because, this is all the way right here. But there's no solution because even roots can't produce negative numbers. You can absolutely try and solve this. What you would get is the exact same solution as before, right? If you try and did everything, but this is negative 3, well, negative 3 to the fourth is also positive 81. So you do all this work, you would get x equals negative 25. But when you plug negative 25 into here, negative 3 times negative 25 is 75, positive 75. Positive 75 plus 6 is 81. Fourth root of 81 is positive 3, but we're saying it's equal to negative 3. However, we can treat it far easier and just say that even roots can't produce negative numbers. Done. That's it. Okay, let's keep going. Fifth root, well, I think you guys get the idea, right? We can mix and match, what we put inside the root and what we put on the outside. But the idea is it doesn't, all the steps are still going to be the same. Only thing that changes is that we raise both sides to the fifth power instead. But from here, again, it is really no different. So again, I'm keeping the inside consistent. I'm keeping the outside mostly consistent. I'm just trying to show that depending on the root, that's all we're going to raise both sides to. Nothing too fancy or too weird. Okay, well, what if we let one side be just a variable? Okay, let's see what happens. Here we have x equals square root of 6x minus x cubed. Here we have square root. So how we undo square root is by squaring both sides. Well, x squared is just x squared. Square root and squared cancel each other out. All right, well, this is just a linear equation. Or not a linear, a regular equation. Let's bring everything to one side. I'm going to bring everything to the left. If you want to bring everything to the right, that is not wrong. You'll get the exact same answers. Let's subtract 6x and add x cubed on both sides. So here, we're a little jumbled. Let's just rewrite terms in order. And now, let's see what happens. Here, we can factor out an x. And, this is also nice, easy, and factorable. And now we're just back to an equation with 3 factors. Set x equal to 0, set x plus 3 equal to 0, set x minus 2 equal to 0. While x equals 0, no work to do there. Here we can subtract 3. Here we can add 2. And we get 3 answers. So we're done, right? 3 answers. No big deal. We haven't run into any problems with checking answers before, have we? Maybe we should check our work. You can take a second and think about which one might be the problem. But let's try negative 3. Well, we plug in negative 3 and, we get a square root. We get an even root equals a negative number. Square roots can't produce negative numbers. Even roots can't produce negative numbers. So negative 3 doesn't work even if you wanted to. 6 times negative 3 is negative 18. Negative 3 cubed is negative 27. Negative 18 minus negative 27 would be negative 18 plus 27. And negative 18 plus 27 is 9. Square root of 9 is not -3. So our only answers are x equals 2 and x equals 0. So, you might not always need to plug in everything, but the second that you run into problems that very generally, have like domain issues, right? Like square roots can't produce negative numbers. Cube roots different. But for example, here, we get right away that we can't have a negative outside a square root like that, or equal to a square root, I should say. And like for the other ones, for rationals, we couldn't have 0 in the denominator. So just look out for things like that. Beyond just, does my answer, when I plug it in, does it actually work, numerically? All right, well, here, let's do it again, but we have -x equals square root of 6x minus x squared. So right away you say, oh, -x, square roots can't produce negative numbers. So we're done, right? Let's see. Let's square both sides, right? This is square root, so let's square both sides. -x squared would be +x squared. Square root and x squared cancel out. All right, well, let's see what happens. Let's bring everything to the left-hand side. I'm going to add x squared and subtract 6x again. Well, here we get x squared plus x squared, that is 2x squared. 2x squared minus 6x equals 0. We can factor out a 2x. This is now two separate factors multiplied to 0. We can divide 2, add 3, and we get 2 answers. And let's see what happens. Well, if we plug in 3 again, oh, would you look at that? We're left with a -3 equals square root of some answer. Also, I don't know why these are cubed. These should be squared. That's a mistake, but it doesn't change the problem at all. Square root still can't produce negative numbers, so we don't run into an issue. Well, we run into an issue, but it's an issue we can easily pick up. When you plug in 3, we get no solution, but notice that 0 is totally okay. So don't be afraid of having negative variables on one side, right? Negative numbers, there's nothing you could do about that. Either it's positive or it's negative on the outside, but when it's variables, we have to treat it a little differently. So just be on the lookout for that. All right, let's do x equals cube root of 6x minus x cubed. Well, this is cube root, so let's cube both sides. X cubed equals 6x minus x cubed. Well, we can bring everything to one side. I'm going to bring it all to the left-hand side. Only difference here is that we now have 2x cubed. Well, we can still factor out a 2x, and we get x squared minus 3 on the inside. Well, let's set each one equal to 0. Here, we're just going to divide by 2, no big deal. But here, let's add 3 to both sides. Let's take the square root of both sides. But don't forget, when we take square roots of both sides, we get plus and minus square root of that answer. So we get 3 answers. Go back and check them on your own, but there are not any issues here. Okay, finally, we get one that all of them work out. So, okay, let's do another one. Why not? I don't remember how many solutions there are or how many questions there are. That's fine. Same thing. We got -x on the outside, cube root. Let's raise both sides to the 3rd power. But here, -x cubed would be -x cubed. Let's again bring everything to one side, but I'm just going to add x cubed this time. I'm not going to bring everything. Let's just add x cubed to both sides. And we did that because, oh, look at that. That's just going to go away. That's pretty nice. Oh, and we only get one answer this time. Just dividing 6 on both sides will give us x equals 0. So that's an interesting problem. Okay. Kind of weird. That's fine. So lots of different examples. But what happens as soon as we have something like this? And what I mean by this is we got a square root and then an extra +1 on the outside. Well, one thing I want to stress is this. Every single problem we've done so far has been just that root on one side by itself. And you can immediately jump to squaring or cubing or to the 4th of both sides. But the second that the square root or whatever root, whatever radical is not on its own, you need to get it on its own. You cannot square both sides when it is like this, because if you were to square this, this is a plus b squared, and that would be something you need to FOIL. And it wouldn't even get the square root out of there if you had to FOIL. So please be careful. When you are dealing with radical equations, make sure the radical is by itself. So all we're going to do here is subtract 1 on both sides. And now we can square both sides to get rid of the square root, but notice this. This isn't just a plain number. This isn't just a single variable. X minus 1 squared is x minus 1 times x minus 1. This requires FOILing. So very different from when there's only one thing on one side. Only one thing on one side, you raise it to the third power or whatever, and you're done. But that's not what happens here. This requires us to FOIL x squared minus x minus another x minus 1 times negative 1 is plus 1. Let's combine like terms. And now we can solve it like, a regular single equation, but we had to make sure that we did that FOILing part. So please don't forget rules of algebra. Don't forget rules of multiplying polynomials that we did all the way in P3. If you forget stuff like that, you're going to be in trouble. Let's bring everything to one side. Let's subtract 2x. Let's subtract 1. All right, after we combine, 1 and negative 1 goes away. Negative 2x and negative 2x becomes negative 4x. And now from here, factor out x, set each one equal to 0. We get 2 solutions. All right. Well, what would this problem be without an extraneous solution? Which one do you want to plug in? I don't know. Let's plug in 0. Let's try what happens when we plug in 0. Well, 2 times 0 is 0. 0 plus 1 is 1. Square root of 1 is 1. And then 1 plus 1 is 2. But 2 doesn't equal 0. So this is actually an even different type of problem, and a problem that you might run into more if you just get the wrong possible answers. So beyond just, we can't have square roots of negative numbers, and square roots can't produce negative numbers, and we can't have zeros in the denominator, it's possible you get one that just doesn't work out nicely for this type of reason, where when you plug it in, both sides literally just do not equal each other. And that is totally okay. There is nothing wrong with that. So x equals 4 is our only solution, because plugging in x equals 0 does not work for us. All right, well, kind of similar. Here we have square root of 5x squared minus 10x plus 9 with minus 2x plus 1 on the outside. Same thing. We need to get the root by itself. So let's add 2x to both sides. Let's subtract 1. And now we can square both sides. But this is, again, FOILing. It is not just say 2x squared minus 1 squared. No. This is 2x minus 1 times 2x minus 1. So let's FOIL that. 2x times 2x is 4x squared. 2x times negative 1 is negative 2x. Negative 1 times 2x is negative 2x. Negative 1 times negative 1 is positive 1. Negative 2x minus 2x is negative 4x. All right. Lots of adding and subtracting on both sides. Let's subtract 4x on both sides. Add 4x. Subtract 1. All right. 5x squared minus 4x, 1x squared. Negative 10x plus 4x, negative 6x. 9 minus 1 is 8. Oh, that actually worked out pretty nicely. It's almost like this is a presentation problem. Factor, set each one equal to 0, solve each one, and we get 2 answers. And I think both of them work out. Yeah, how about that? All right. One more crazy example. You're not going to see one like this all that often. But what if we have 2 roots? Oh no, the world is going to end, it seems. Don't worry. When you have multiple roots, what our goal is here is to get one root by itself first, and then we're just going to need to do the process twice. So here's what I mean. Let's add square root of x minus 1 to both sides, so that square root of 2x minus 1 is by itself. Well, what we're going to do is square both sides to get rid of this root. It's not going to get rid of this root, but that's okay. All it means is we're just going to need to do this twice. So let's square both sides. And again, this square root and squared goes away, but 1 plus square root of x minus 1 is foiling. So that square root cancels out. And now let's FOIL. 1 times 1 is 1. 1 times square root of x minus 1 is square root of x minus 1. Square root of x minus 1 times 1 is square root of x minus 1. Square root of x minus 1 times square root of x minus 1. Oh, square root of anything times itself is just itself. Square root of x minus 1 plus itself is going to be 2 of them, right? If we're multiplying them, square root of x minus 1 times square root of x minus 1, it's just itself. But when we are adding, it is 2 of them. Be very careful. All right, so lots of simplification we can do here. 1 minus 1 goes away. Let's bring this plus x to the left-hand side. Let's subtract it on both sides. 2x minus x is just x. And now the root is mostly all by itself. What you can do is you can divide by 2 and then square. But what you'll see is when everything is multiplied together, it's actually okay for us to square it, right? Because if this was 2 plus square root of x minus 1, well, then we would need to FOIL. But 2 times square root of x minus 1 is just 2 squared, which is 4. Square root of x minus 1 squared is just x minus 1. Here, we got a FOIL on the left-hand side. X times x is x squared. X times negative 1, negative x. Negative 1 times x, negative x. Negative 1 times negative 1, positive 1. And distribute 4. All right. Combine like terms on the left. Negative x minus x, negative 2x. Let's subtract 4x on both sides. Let's add 4 to both sides. Negative 2x minus 4x, negative 6x. 1 plus 4 is 5. Factor, set h1 equal to 0. And we get 2 answers. So radical equations, not so totally radical as I had in the beginning. They can get kind of messy, but they end up kind of all being similar situations. All right, let's get out of radical equations and let's start talking about something a little different. Okay, so let's talk about rational exponents. Now, rational exponents are just fraction exponents, right? Rational equations, fraction equations. Rational exponents was the end of P6 where we had a fraction in our exponent. So let's say we had something like 3 over 2 as an exponent. Well, in 3 over 2, what that's saying is square root of something, the denominator is 2, square root, but then the numerator was 3, so that's cubing. So basically, numerator is what we're actually doing to the thing. Denominator is what kind of root are we taking. And we're going to use a lot of that today, or in this subsection. So say we have some expression u to the a over b equals c. Well, kind of think about this. When we were doing square roots, we squared both sides. And when we're doing squared, we square root both sides. And we know square root is like 1/2. So what we're going to do is something very similar, except instead of trying to think about it in terms of roots and cubes and all that, what we're going to do is just raise both sides to the reciprocal power. However, we need to keep something in mind, that if we raise both sides to the reciprocal, what the value of a is matters. Because think about this. If this is 3 over 2, we're raising both sides to the 2 over 3. When we raise both sides to the 2 over 3, that's saying take the cube root and then square it. But if this is 2 over 3 and we raise both sides to the 3 over 2, that's like saying take the square root of both sides and then cube it. But remember what happens when we take square roots of both sides. So what this ultimately boils down to is this. All right, so if this original numerator is odd, nothing weird happens. You raise both sides to the reciprocal power, so you raise both sides to the b over a. That gets rid of it for u, just like square roots and squared, it just gets rid of that. But on the other side, you get c, whatever that constant is, to the b over a. And I've already told you that to the b over a is basically saying 8th root raised to the b. But if a is even, well, we pick up an extra plus and minus. Again, if this original numerator is even, let's say 2, that means that when we raise both sides, the 2 ends up in the denominator, but that is like taking a square root. So, again, long story short, if original numerator is odd, nothing weird happens. If original numerator is even, pick up a plus and minus. So you could take these two things as a rule. If a is odd, raise both sides to the reciprocal, and then do, denominator, new denominator, raised to new numerator, and same thing here, but when it's even, plus and minus. All right, maybe that's kind of wordy, kind of complicated. Let's do a bunch of examples. X to the 3 over 5 equals 8. So what we're going to do is raise both sides to the reciprocal power. Well, this is 3 over 5, so we're going to raise both sides to the 5 over 3. Okay. But now what we need to look at is this original numerator of our exponent. If the original numerator is even, we pick up a plus and minus. But if the original numerator is odd, nothing happens. So original numerator even, plus and minus. Otherwise, no. Okay, well, this original numerator is 3, and 3 is odd. So we do not pick up a plus and minus, but we still raise both sides to the 5 over 3. Okay, well, that's so far the new part, but it's been a while since we've talked about rational exponents, so let's look at this a little bit more. 3/5 and 5/3, well, that cancels out. That's the whole point. But what this says is 8 to the 1/3 to the 5, right? Exponent raised to an exponent. We could multiply those exponents to get back to 5/3, but this is like to the 1/3 and then to the 5. Well, to the 1/3 means cube root. Cube root of 8 is 2. 2 to the 5th is 32. So denominator root, numerator power. So this says cube root and then raise it to the 5th. Cube root of 8 is 2. 2 to the 5th is 32. Okay, well, let's do more examples of this. Another thing I want to stress is that, if your rational exponent part is not by itself, get it by itself, just like other things we've done before. In a lot of cases, these things that we want to apply, they need to be by themselves on one side for us to be able to do that. So let's add 30 to both sides. Let's divide both sides by 2. And now we can finally, do the rational exponent step. This is to the 3 over 2. So we're going to raise both sides to the 2 over 3. And again, this original numerator, this 3 up here, can I highlight just that? I did it before. Okay. The original numerator was 3. 3 is odd. Nothing weird happens when it is odd. Okay, so we're going to raise both sides to the 2/3. To the 2/3 says cube root first and then squared. So cube root of 27 is 3 and 3 squared is 9. Oh, but don't forget, the thing that had the rational exponent wasn't just x, and that's okay. So 2x minus 1 equals 9. You know how to add 1 to both sides. You know how to divide both sides by 2, and you get x equals 5. Okay. Well, let's start doing things where things actually start to happen and things that are weird. Well, here, you already see we're going to raise both sides to the 3/2. However, this original exponent's numerator is even now, right? Previous two cases, let me go back to them really quick. Here, this is 3 over 2. Numerator was odd. Nothing weird happened. No plus or minus happened when this was odd. But for the first time, we have an example where this numerator is even. If the original numerator is even, we pick up a plus and minus. Again, when we raise both sides to the 3/2, this is like saying take the square root of both sides and then cube it. And we remember from 1.3 that when we are taking the square root of both sides, we pick up a plus and minus. All right, so 4 to the 3/2 says take the square root first. Square root of 4 is 2. 2 cubed is 8. And now we just get two equations. 3x minus 1 equals positive 8. 3x minus 1 equals negative 8. Add 1 to both sides. Divide both sides by 3. And we get two solutions. Okay. So a little messy, but really not all that much of an extra step. I mean, yes, it created two separate problems for us at the end, but I think by now, solving equations like this, we absolutely love. So again, it all comes down to the original exponent. So here we got to get 2x plus 1 to the 4/3 by itself. Let's add 7 to both sides. And now we're going to raise both sides to the reciprocal of 4/3. That would be 3/4. But this original numerator is even. So if it is even, we pick up plus and minus. So 16 to the 3/4. Okay, 16 to the 3/4 says take the 4th root and then cube it. So 16 to the 1/4, 4th root of 16. 4th root of 16 is 2. 2 cubed is 8. And now we again have two equations. 2x plus 1 equals positive 8. 2x plus 1 equals negative 8. Subtract 1 and divide by 2. And we get two answers. So again, one more time. Original numerator odd, no plus and minus. Original numerator even, yes, plus and minus. All right, let's do two more examples. 5x minus 14 equals 3/800. We're going to raise both sides to the 800/3. However, original numerator is odd, no plus and minus. So we raise both sides to the 800/3. Well, very convenient. 1 raised to any power is just 1. You add 14, you divide by 5. How beautiful. But if the original numerator is even, 800, we pick up plus and minus. But still, 1 raised to any power is just 1. So just two separate equations. Add 14 to both sides. Divide both sides by 5. And you get two solutions. So that's rational exponents. Not really much else we can do with them right now. And maybe we come back to those in a little while. But one more small part, quadratic likes. The thing with quadratic likes is kind of interesting because you will see stuff like this in the future. It's just kind of annoying. You're going to see why in just a second. It requires a very well-seasoned mind to recognize some of these things. I don't think any of these are so obvious that you're going to look at it and be like, oh, yeah, I see it right away. So just getting in the habit of noticing these type of things is definitely the key to doing quadratic likes. But again, you're going to find all sorts of stuff like this. So just keep an eye out for them. So for example, let's say we have x to the 2/3 minus 5x to the 1/3 plus 6. Well, here we have an x to the 2/3, and this is like x to the 2 minus 5 x to the 1 plus 6. Only weird thing is that we have these extra, 2/3 and 1/3. Well, what if we rewrote x to the 2/3 as x to the 1/3 squared? Well, now this is like something squared minus 5 times something plus 6. It's quadratic like x squared minus 5x plus 6. Only thing is that our variable isn't x, it's x to the 1/3. Well, we don't want to just magically substitute x in because that kind of screws up what we're looking at. Instead, let's say x to the 1/3 is u. We like using u to substitute things a lot of the time. If you end up taking Calc 2, you might even come back to u substitution, but that's a long time from now. All right, so wherever we see x to the 1/3, let's instead call it u. All right, well, x to the 1/3 would be u squared minus 5 times u plus 6 equals 0. Oh, well, if I gave you this, you would know to factor, you would know to set each factor equal to 0. But here's the thing. We're saying that u equals 2 and u equals 3, but we're not solving equations that are u. We're solving an equation that had x in the beginning. So we substituted u in for x. However, we're not solving a u equation. We need to resubstitute whatever we substituted in as u. Well, I have it here that u is x to the 1/3. So this isn't u equals 2. This is x to the 1/3 equals 2. This isn't u to the u equals 3. This is really x to the 1/3 equals 3. Now, from here, you know how to solve these equations from the last step. We'll just cube both sides, and we get 8 and 27. And those are our two answers. So quadratic likes just introduce this one like kind of intermediate process of just saying, let's solve an equation that looks very similar, and then just resubstitute in the thing we initially substituted. And that's essentially what quadratic likes are. Okay, this video is probably very long. I don't want to go super crazy into doing this, but here you might also notice something squared minus 6 times something plus 8. Well, u, if we say, is x plus 1 over x, well, then this is like u squared minus 6u plus 8. And you know how to factor this. You know how to set each factor equal to 0. So we have u equals 2 and 4. But if u is x plus 1 over x, what we're really going to get is x plus 1 over x equals 2, x plus 1 over x equals 4. All right. Something like this is way crazy. It's more just, to show you the process. From here, to solve each specific part, you would multiply everything by the least common denominator, x. X squared plus 1 equals 2x. Subtract 2x. Factor. Set each factor equal to 0. You get 1. But for the other one, yeah, this is not nearly as pretty. You do the same thing, and now you have to do quadratic formula. So if you want to watch the whole thing, feel free to slow it down. But essentially, we had 2 separate branched equations, and then we got 3 separate total answers. So just something to keep in mind. Again, you could slow down the video to watch all those steps, but once we've set up each specific part, they become equations that we've already talked about. So that's the end of 1.5. Kind of long, kind of showcase. 1.6 and 1.7 are not nearly as long. What we've done in 1.1 to 1.5 has been equations. We're going to learn to solve inequalities in the next section. And then 1.7 is a nice way of going out. We're just going to introduce absolute values to equations and equations and inequalities. So that's the end of 1.5, and I will see you in 1.6. Bye. Hi, everyone. Welcome back to 1.6. So chapter 1 in general is about solving equations. However, we do kind of change gears for the last 2 sections and start to solve inequalities. So the whole chapter is technically solving equations and inequalities, except the first 5 sections has been solving equations. So we could solve inequalities now. And the only thing is that we have a slightly different way of referencing our answer, but the way we solve inequalities is almost identical to how we solve equations. So here in 1.6, we're just going to start solving inequalities. And then when we get to 1.7, it's just a little bit different. We just introduce some new properties that revolve around absolute value. But for now, let's talk about inequalities. So inequalities in general are expressions that describe the relationship between any 2 numbers. But what we're going to do here is have an expression that describes the relationship between a variable and some number. So previously we had x equals a finite set of disjoint numbers, right? Like the very last example in 1.5 said our answer was 2, 1 plus square root of 3 and 1 minus square root of 3, something like that. Three values that are all very different. And even if we didn't get weird answers like -3, 0, and 2, they're still disjoint. However, what we're going to have for inequalities is a solution set. And a set is just a set of values that make the inequality true. Now, you can say that equations also have a solution set. Only difference is now our solution set is going to be this nice, smoother set of continuous values. So it's a lot easier to satisfy an inequality than an equation. In an equation, we are forcing things to be equal to each other. But now in inequalities, we're just saying, well, one side can be bigger or one side can be greater than or equal to. So we have a little bit more leniency when it comes to that. It just means we're going to need to write our answer in such a way. So we also have 3 different types of inequalities that are all very, very similar to equations that we had in 1.1. In 1.1, we had conditional equations, inconsistent equations, and identities. And the same thing is true here for inequalities. An inconsistent inequality is just any inequality that is never true. An identity inequality is just any inequality that is always true. And conditional inequality is just any inequality that has one particular set of answers. So we use all of these words for equations. We can talk about them in terms of inequalities, but again, not really worried about you naming them, more interested in you being able to actually do something with them. So solving inequalities, like I said, is a lot like solving equations, except we have one added rule, only one. That added rule, aside from, writing our answer different, the rule itself, the only difference is that when we are multiplying or dividing by negative numbers, we need to flip the sign of our inequality. So let's talk about that. If you are doing anything in your inequality, it is functioning exactly like solving equations. However, in the very specific scenario that you have to multiply or divide by a negative number, you have to flip the inequality sign. Less than would become greater than would become less than, and so on for the greater than or equal to, less than or equal to. That's the only added rule when it comes to inequalities. So let's just get into doing examples. 2x plus 5 is greater than 3. And again, we solve these exactly like we solved equations. If this was an equation, you would subtract 5 on both sides. You would divide both sides by 2. But again, we got to be very careful when we're multiplying and dividing numbers. In this specific case, we are dividing by positive 2. When we divide by positive 2, we do not change the sign. Okay, well, -2 divided by 2 is just -1. Now, again, only added step, not an added rule, the added step to solving inequalities is that we need to write this as an interval. So we have been doing that all the way since P1. So x is greater than -1 says -1 and everything bigger than it. Specifically for just greater than, we're going to use parentheses. Don't forget that if it was greater than or equal to, we would use a bracket. So, and also parentheses for infinity and negative infinity. Infinity will never have a bracket. Negative infinity will never have a bracket. So just keep an eye out for stuff like that. And again, if you need inequality help, go back and check out the P1 presentation. Okay, 8 minus 3x is greater than or equal to 2. Again, if this was an equation, you would start by subtracting 8 on both sides, and then you would divide by -3. Except, however, we have the added rule that if we are dividing by -3, we have to flip the sign from greater than or equal to less than or equal to. And then from here, okay, -6 divided by -3 is +2. X is less than or equal to 2 says everything to the left of 2. And 2 included because of the less than or equal to. So -infinity up to 2. Okay, let's keep going. 7x minus 11 greater than or equal to 2 times x minus 3. If it was an equation, you would distribute 2. You would subtract 2x on both sides. You would add 11 to both sides. You would divide both sides by +5. And if we are dividing or multiplying by positive numbers, nothing changes. It only changes for negative numbers. So we get x is greater than or equal to 1. x is greater than or equal to 1 says everything bigger than 1 with 1 included. So from 1 to infinity. Okay. 7 minus 2x is less than negative 3. All right. Again, if it was an equation, you would start by subtracting 7. You would then divide by negative 2. But again, that's the key here. We're dividing by negative 2. So if we divide by negative 2, we have to flip the sign. Less than becomes greater than. And negative 10 divided by negative 2 is positive 5. X is greater than 5 says 5 and everything bigger than it. Okay, and parentheses for 5 since we have strictly greater than. Okay, 7 times x plus 2 minus 20 minus 4x is less than 3x minus 1. Okay, let's distribute 7 here. Let's distribute 3 here. And let's combine like terms. 7x minus 4x is going to be 3x. 14 minus 20 is going to be negative 6. And maybe if you have the foresight from 1.1, you already start to notice something is wrong. Well, let's combine our x's. So let's subtract 3x on both sides. Well, when we do that, it happens to go away and we're left with just negative 6 is less than negative 3. Okay, this is kind of weird. When we were dealing with equations, don't forget that when we were dealing with equations, if we got to a point that the statement was always true, 0 equals 0, 2 equals 2. When we got to a statement that was always true, that was the definition of an identity. And likewise, if we got to a statement that was never true, we called that an inconsistent equation. And same thing is true here for inequalities, except don't forget, we look at inequalities a little different from equations. So yes, if we had negative 6 equals negative 3 equals, like in equations in 1.1, we would say that was not true. But don't forget, this is an inequality. We need to determine if the inequality is true. Now, the question we ask, is negative 6 less than negative 3? Is negative 6 to the left of negative 3? And that is always true. So yes, maybe the values don't equal each other, but we're not looking for equals. We're looking for less than. And this inequality is true. If the inequality is always true, we say the solution set is all real numbers, negative infinity to infinity. No matter what we plug in for x, this inequality will always hold true. Okay, well, you could probably guess what the next one's going to be. So here, let's distribute 2. Let's distribute 5. Let's combine like terms. 2x plus 3x. 2 apples plus 3 apples is 5 apples. Negative 5 plus 3, you're $5 in debt, and I give you 3. You are now only $2 in debt. Well, let's subtract 5x on both sides, and that goes away on both sides, and we get 10 is less than negative 2. So again, it's not a matter of if these values are equal. We saw that in the last case, those values weren't equal, but we're looking for, satisfying an inequality, not satisfying an equation. And now I ask, is 10 less than negative 2? Is this inequality true? Well, 10 is definitely never less than negative 2. That's never true. So there is no solution. We would call this inconsistent. We would call the last one an identity, but it's more interesting for us to say what the solution set is. For inconsistent, more interesting for us to say no solution. Okay, so solving inequalities, I don't think all that crazy. Well, we're going to introduce another type of inequality called compound inequalities, where all it is we have multiple inequalities going on at the same time. Now, that's actually an interesting question, because if we have multiple inequalities at one time, are we looking to satisfy both? Are we looking to satisfy one or the other? And that brings us to this really interesting logic question. So this is a question you would you would study in the study of logic, logical mathematics. So it's the difference between and or. And there's a very big difference when we're talking about English and mathematics and likewise for or. So here's what I mean by that. If we're talking about English, if we're speaking, to each other, not in a mathematical sense, of course, because Most people don't do that. But so let's say I'm going to my friend's house Friday and Saturday. What does that mean to you? That means that I'm going to my friend's house on Friday as well as Saturday. I am going both days. However, if I say I'm going to my friend's house Friday or Saturday, what we think is that I would go to my friend's house Friday or I will go Saturday, but I won't do both. And that's different from mathematics or. And yes, that's different from mathematics or. So English and says both need to be true. English or says that only one of them should be true. But mathematics and an or works like this. Well, mathematics and functions the exact same way. If we're saying two things and both of them need to be true for it to be a true statement. However, mathematics or doesn't say one or the other, one either or. Mathematics or says at least one of those things need to be true. So if we're thinking mathematical or to my original statement, I am going to my friend's house Friday or Saturday. Now, mathematical or would be satisfied if I am going Friday, if I'm going Saturday, or I'm going both. So mathematics or is also satisfied in the case that it is and. So if I go at least one of those 2 days, I could go Friday, I could go Saturday, or I could go both days. We say go both days is and, but mathematical or says one or the other or both, and that would satisfy. So that's kind of complicated, right? This isn't the study of logic. This is the study of college algebra. So what we eventually bring this to is that or will be a union of intervals, right? If we're looking at two separate inequalities, we solve two separate inequalities. If we're throwing an or in between them, all we're doing is taking the union of those things, having one, having the other, union together, whereas and will be an intersection. So that's where it comes down to, but it's a good example to talk through. Let's get right into compound inequalities. So let's say we have 2x plus 7 is less than or equal to 1, or 3x minus 2 is less than 4 times x minus 1. So here's what I mean. What we do is we're looking for a set that if we plug in a value to both inequalities, at least one of them is true. So let's say, you know what, let's do the example first. So if we're doing or, we still solve each one separately. We're still going to distribute 4. We're still going to combine x's. We're still going to subtract numbers. And we're still going to divide by constants. So first one, we divide by 2. Second one, we divide by -1. But don't forget, when we divide by -1, we have to flip the sign. Okay, x is less than or equal to 3 says everything to the left of that should be a 3. Everything to the left of 3, and x is greater than 2 says everything to the right of 2. And now what or is telling us is that we are taking, oh, no, this should be the -3. My apologies. This should be the -3 right here. Okay. What mathematical or is telling us is that we want to take the union of these two things. So we just take those two intervals and put a union sign between them. Basically, that's basic. There are cases where it's actually a little simpler than that. We can, combine it into one, but everything to the left of -3 and everything to the right of 2 don't have anything in common. So here's what or is saying. It's saying that we can choose any value in this solution set, and at least one of these two things is true. Maybe not necessarily both of them, but at least one of them is true. So for example, if we plug in -5, well, 2 times -5 is -10, -10 plus 7 is -3, and now -3 is less than or equal to 1. So this is satisfied. Okay, well, if we plug in -5 here, 3 times -5 is -15, -15 minus 2 is -17, okay? -5 minus 1, -6. 4 times -6 is -24. I think we said -17 on this side is less than -24. Well, that wouldn't be true, but that doesn't matter. Only one of them needs to be true. At least one of them needs to be true. So when we plug in -5, this statement's true, but even though this statement isn't true, the OR says one of them is true. We're good to go. Okay. And same thing if you were to plug in 3, this one would be satisfied, this one would not. However, let's say we plug in 0, a value that isn't in the solution set. If you plug in 0, 2 times 0 is 0, 0 plus 7 is 7, and 7 not less than or equal to 1. So this one wouldn't be satisfied. Well, for us to satisfy this entire mathematical statement, that must mean that this one is satisfied. Let's see. 3 times 0 is 0. 0 minus 2 is -2. 0 minus 1 is -1. 4 times -1 is -4. So is -2 less than -4? No, neither of them were satisfied. But we knew that because 0 wasn't in our solution set to begin with. Okay, let's do another OR one. 3x minus 5 is greater than or equal to 7. 5 minus 2x is greater than or equal to 1. All right, let's add a constant to both sides. Let's divide by 3 and -2. Don't forget that when we divide by -2, we have to flip that sign. And we get x is greater than or equal to 4. X is less than 2. Okay, well, those are the intervals. Everything bigger than 4, everything less than 2. And OR says take the union of them. And just make sure you write your answers in order. For example, 4 to infinity would be to the right of -infinity to 2. -infinity up to 2, and then 4 to infinity. Technically, you wouldn't necessarily be super wrong by writing just this, but for the case of what we're trying to talk about, or we want to make sure we're taking the union of these things. Well, now let's do and. And at the very end is identical, except we take the intersection of them, everything they have in common. Okay, so we're still going to solve each inequality the same. Let's distribute 2. Let's distribute 3. Let's combine some constants. Let's add or subtract constants on both sides. And now you know that we need to divide by 2 and divide by -3. And don't forget, we divide by -3. We're going to flip that sign. All right, so this says everything to the left of 5. This says everything greater than -2. And now what we want is the intersection of these things. What do they have in common? Okay. I'm going to go to the whiteboard just for a moment, just to show you what this one looks like. I'm not going to do it for the next one, but just so you have an idea. Okay, so just to give the brief example of what an intersection would look like for intervals, since we didn't really do it in chapter P, we had -infinity to 5, -2 to infinity. So if we were to draw these on a number line, first one would be everything to the left of 5. And the second one would be everything to the right of 2. So if we want to take the intersection of these two things, it would be everything they have in common. Well, let's draw some spots right here. And we see the only thing that these two both have in common is this section in the middle. Well, what's this section in the middle? -2 up to 5. Everything to the left of -2 isn't true because everything to the left of -2 is not between -2 and 5. And same thing we could say for here, does not count here. So the answer to this intersection would be -2 to 5. So I'm going to go back to the presentation. Okay, so we get our answer to be -2 to 5. So for the next one, I'm not going to go back to the whiteboard and draw it, but it's good practice for you if you want to practice drawing intersections. So what we're saying is that this is the solution set. -2 to 5 is the solution set. That means if it's in the solution set, it will satisfy both things. That's the definition of OR. We need both of these to be satisfied for and. So let's say we take 0, which is in the solution set. 0 minus 3, negative 3. 2 times negative 3 is negative 6. Negative 6 plus 5 is negative 1. And negative 1 is less than 9. That part is true. If we plug in 0, 1 minus 0 is 1. 3 times 1 is 3. 3 minus 2 is 1. 1 is less than or equal to 7. So a value in our solution set satisfied both. And that's the key to and versus or. And you have to satisfy both. Or you only need to satisfy one of them. You can satisfy both, but you only need to satisfy one of them. So it's a little less restrictive. Now, if we were to plug in a value that is not within our solution set, let's say we plug in 6. Well, 6 minus 3 is 3. 2 times 3 is 6. 6 plus 5 is 11. 11 less than 9 is not true. 11 is not less than 9. So this one fails. And by definition, for and, the whole thing fails. Even though when we plug in 6, 1 minus 6 is negative 5. 3 times negative 5 is negative 15. Negative 15 minus 2 is negative 17. Well, this inequality would be true, but since it's not true in both, it doesn't count. So our solution set is the intersection of each individual part's final answer. Okay, let's do another and example. Again, you can draw it on your own, but let's do it. Here, let's distribute 2. Let's combine some constants. Let's add or subtract some constants. Let's divide by negative 2 and 2. Don't forget here, when we divide by negative 2, we got to flip the sign. This says everything bigger than negative 1 with negative 1 not included. This says everything less than 3, 3 included because of the less than or equal to. So now, what are all the numbers that are in common from negative 1 to infinity, negative infinity to 3? You could practice drawing it on your own, but that would just be everything between negative 1 and 3. So for example, if you plug in 0, 3 minus 0 is 3, 2 times 3 is 6, 6 minus 3 is 3, 3 is less than 5. That one's true. 0 minus 5 is negative 5. 2 times negative 5 is negative 10. Negative 10 plus 7 is negative 3. Negative 3 is indeed less than or equal to 3. So everything in the solution set is true. Everything outside of the solution set would not be true. Try something outside of this solution set to prove to yourself that at least one of them fails. So again, for or, we're looking for a union at the end because only one of the two statements needs to be true. But for and, we're looking for an intersection because both of the things need to be true. All right, we can also have compound inequalities that look like this. Now, we're going to look at inequalities that look like this again in the next section. So it's important that we solve it here, but actually solving inequalities like this is actually really, really nice. So what it turns out is that this type of inequality is actually an and inequality in disguise. However, when it's written in this way, so much easier to solve. Okay, when we're doing equations, or when we learn to do equations, we said we needed to subtract 3 on both sides. But never in equations did we have 3 parts. It didn't make sense to have this part equal to this part equal to this part, right? If they're equal, everything's going to be equal. So for inequalities, it's a little different because notice in all the questions we've done so far, there have been bounds to where our answer starts and ends in a lot of these compound inequality cases. So long story short, when you're solving inequalities that look like this, if you do something to one part of the inequality, you need to do it to all of the parts of the inequality. So when you go to subtract 3 to get x by itself, you're not just subtracting the inside part and one of the two sides minus 3. You are subtracting everything by 3. Okay? You subtract 3 everywhere. And now when you go to divide by 2, you divide by 2 everywhere. So we get negative 4 less than x less than or equal to 3. Well, if you were to draw all the values between negative 4 and 3, that would just be the interval. Negative 4 not included because of the less than, but 3 included because of the less than or equal to. So way easier to get a solution set. So if you plugged in something between -4 and 3, you would get this entire inequality is true. Let's plug in 0. 2 times 0 is 0. 0 plus 3 is 3. -5 less than 3. That's true. 3 less than or equal to 9. Also true. Okay, so these are actually pretty nice. Let's do another one. Maybe we see this -4x. That's going to be a problem. Let's see what happens. We want to subtract 2 to start, but make sure we subtract everything by 2. Okay, we're going to divide by -4, but make sure when you divide by -4, you divide everything by -4. But also, we know that when we're dividing by negative numbers, we need to flip the sign. Well, in this case, we're going to flip both signs. So this less than will become a greater than, this less than or equal to will become a greater than or equal to, and now we get this. This is kind of ugly though. 2 is to the left of -3. That's not what the inequality is saying, but it's written to the left of -3. Ugh, that's not good. Here's what we're going to do. To solve this problem, all we need to do is just read it backwards. And what I mean by that is literally -3, instead of reading this as greater than or equal to, if we're reading it backwards, this is then -3 is less than or equal to x, which is less than 2. That's all it means to read it backwards. Literally go piece by piece and just read it backwards. Well, now from here, saying -3 to 2, not so shabby. Again, if we were to plug in something outside of the solution set, we've seen so many times outside of the solution set works, inside the solution set works. Let's plug in something outside. Let's plug in 3. -4 times 3 is -12. -12 plus 10 is -10. -6 less than -10. Oh, well, that's not true. So part of this fails. -10 is less than 14, but it doesn't meet that first bound criteria. So something like that. So inequalities, a lot like equations. Compound inequalities, also a lot like equations. Whole thing is just kind of like its own weird rule. And there exists one more type of inequality that we can solve when it comes to like rational inequalities, right? Where just one side is a fraction. So not super common here in algebra, but something like this is actually going to be very popular when you go to solve increasing, decreasing, and for extrema and concavity, all very fancy words in Calc 1. So I'm going to do some examples here, but odds are you're not going to do a ton of them in your classes, no matter where you're watching this. But if you're watching this for Calc 1, you definitely want to listen up. If I ever decide to make Calc 1 videos, I'll do those separate. But yeah, for now, let's do test point method. So we want to use it for anything not linear. So for example, quadratic, rational, etc. The steps are as follows. Make sure one side is equal to 0. We have to make sure one side is equal to 0. We're going to simplify everything as much as possible. And we're going to set the numerator and denominator, if we have it, equal to 0. We want to find all the locations where the numerator is 0 and where the denominator is 0. We're going to put those values on a real number line, which create multiple subintervals. Okay. And we're going to test values in those subintervals by plugging them into the original equation or an equivalent simplified version that we find, right? Our final answer is all the subintervals that are true, and we're going to ignore all the ones that are not true. So the last thing we need to do is make sure that the endpoints are either included or not included, parentheses versus brackets. These are a lot of steps. Let's just do some examples. So I'm going to move to the whiteboard, and I will see you in just a moment. Okay, so here we are on the whiteboard. Let's do x squared plus 4x greater than or equal to 5x plus 6. Step 1, we need to get 0 on one side. So let's start by subtracting 5x. 4x minus 5x is -x. Let's then subtract 6. X squared minus x minus 6 greater than or equal to 0. This side we can factor as x minus 3, x plus 2. And now let's set each one equal to 0. So I know it says greater than or equal to 0, but we just want some reference points. So let's set x minus 3, x plus 2 equal to 0. We're going to set each part equal to 0. So x is 3, x is -2. And now what we're going to do is take these 2 points and put them on this subinterval. I like to put 0 there as a placeholder, but it is not one of our points. Well, notice we have an interval to the left of -2. We have an interval between -2 and 3, and we have an interval to the right of 3. So our 2 points created 1, 2, 3 subintervals. And now what we're going to do is plug in a value in each of those 3 subintervals. And what we want to determine is if our inequality is true. So let's plug in -3 for the first one. Well, -3 minus 3 times -3 plus 2. Well, -3 minus 3 is going to be negative. -3 plus 2 is also going to be negative, and a negative times a negative is a positive, and positives are greater than 0. So our our left interval is true. And notice that I didn't even really care what the values were. I only care about the sign, and that's the benefit to us being greater than or equal to 0, or having whatever with one side equal to 0. If one side's equal to 0, all we're trying to determine is if it is positive or negative. Positive numbers are greater than 0, negative numbers are not. So you can find the actual value if you want, but it's easier to just determine signs. Okay, so we know the left one is true. Let's do the next one. Okay, let's plug in 0 for the middle interval. 0 minus 3, 0 plus 2. Well, 0 minus 3 is negative, 0 plus 2 is positive, but a negative times a positive is a negative number, which is not greater than or equal to 0. So our middle interval is not going to be true. Okay, last but not least, let's check a number to the right of 3. Let's plug in, let's say 4. 4 minus 3 times 4 plus 2. Well, 4 minus 3 is positive. 4 plus 2 is also positive. It is 6, but it's positive. Okay, and a positive times a positive is indeed a positive, and positives are greater than 0. So that is true. So then we know our answer is going to be -infinity up to -2 with 3 to infinity. And now all we need to do is determine which of each of our 4 things, 1, 2, 3, 4, have brackets or parentheses. So to start, -infinity and infinity always get parentheses. Now -2, what we need to do is plug in -2 into our inequality to see if it is true. If it is true, it is part of the answer. We put a bracket. If it is not true, we don't put a bracket. So if we plug in -2, well, what we get, -5 times 0, -5 times 0 is greater than or equal to 0. So -2 works. And then same thing for 3. 3 also works because if you plug in 3 to x minus 3, that is 0. 0 times anything is indeed greater than or equal to 0. So our answer would be -infinity up to -2 with 3 to infinity. That's an interesting looking -infinity, but I know you guys get the idea. Okay, let's do one more example, and then we'll call it a day for this section. Okay, so let's do x squared plus 2x minus 15 over x minus 1 is less than 0. Okay, first things first, we got to simplify everything as much as we can. Numerator, x plus 5, x minus 3 over x minus 1 is less than 0. Okay, so what we need to do now is, even though we have a denominator, we still want to set each and every part equal to 0. Well, we get x equals -5, x equals 3, x equals 1. And you might be wondering, why are we setting 1, x minus 1 equal to 0? Why is 1 part of that? We never want the denominator to be 0. And that is true. However, notice that in what we were doing before, if the denominator was negative or positive, it could completely change what happens in the numerator. So yes, we're never going to actually plug in 1. However, we just got to be a little bit careful. So we set everything equal to 0. All right, let's put all of those values on a number line. We have -5, 1, and 3. And again, I like just putting 0 there as a placeholder. Not one of our intervals, but it's good to put there. We have everything to the left of -5, everything between -5 and 1, everything between 1 and 3, and everything bigger than 3. So our now 3 values created 4 subintervals, and there's nothing wrong with that. Now we're going to plug in a value into each of these 4 subintervals and determine whether or not the inequality is true or false. So I'm going to rewrite the inequality over here. X plus 5, x minus 3 over x minus 1 less than 0. Let's plug in -6 for here. -6 plus 5, -6 minus 3 over -6 minus 1. -6 plus 5 is going to be negative. -6 minus 3 is going to be negative. -6 minus 1 is going to be negative. So we have a negative times a negative is a positive, divided by a negative. Whole thing is negative, and negatives are indeed less than 0. So again, don't care about what the value is. We only care about the signs. Well, all negative numbers are less than 0, so this one's going to be true. Okay, let's do the same thing for x equals 0. That's the wrong thing. Let's do the same thing for x equals 0 to test a value between -5 and 1, and we'll see what happens. 0 plus 5, 0 minus 3, 0 minus 1. 0 plus 5 is positive. 0 minus 3 is negative. 0 minus 1 is negative. Well, negative divided by a negative is going to be positive, or actually we should probably look at it this way. Positive times a negative is a negative, divided by a negative. Negative divided by a negative is a positive, but positives are not less than 0, right? We want less than 0, so this interval not going to be true. Okay, we're almost there. 2 more values. Let's plug in a value between 1 and 3. I think 2 is a great choice. 2 plus 5 times 2 minus 3 over 2 minus 1. 2 plus 5 is positive. 2 minus 3 is negative. 2 minus 1 is positive. Well, positive times a negative is a negative. Negative divided by a positive is negative. And negatives are indeed less than 0. So that interval is going to be true too. Again, it's not a matter of what the value is in between 1 and 3. It's a matter of if we plug it in, is the inequality true? Okay, and we are almost there. Let's test one more. Let's plug in 4. So we plugged in 2 here. All right. Oh, I erased too much. All right. Well, x plus 5, x minus 3, x minus 1 less than 0. All right. If we plug in 4, 4 plus 5, 4 minus 3, 4 minus 1. Well, 4 plus 5 is positive. 4 minus 3 is positive. 4 minus 1 is positive. Whole thing is positive, right? Positive times a positive is positive, divided by a positive is positive. But a positive numbers are not less than 0. So that answer is not true. Okay, that interval is not true, I should say. So our answer is all the correct spots here and here. Well, that would be -infinity up to -5. And then we skip all the way from 1 to 3. Now, you might be wondering why I was so quick to use parentheses. Well, you can go in and check each one, but actually a really good giveaway is the less than sign up here. So if we have a less than or greater than sign, there's no chance that we can ever be equal to 0. So we are always going to use parentheses if this is greater than or less than. So even for the other one, if it was greater than or less than, you could jump to that right away. But if you don't like this, check each value to determine. You would see that if you plug in -5, the numerator is 0. Well, 0 is not less than 0, so that's not true. If you plugged in 1, well, the numerator is going to be 1 squared is 1, 2 times 1 is 2. 1 plus 2 is 3. 3 minus 15 is negative 12. But 1 minus 1 is 0, and then you'd have negative 12 over 0. So that wouldn't work. That would have to have a parentheses because we can't be equal to 1. 3, same argument as negative 5. Top would be 0, but 0 not less than 0. So with that said, that's the end of 1.6. We got one more section in 1.7. It's actually a pretty nice section. We like absolute values. They get a little twisty, but not really so hard to wrangle down. So I will see you in 1.7. Bye. Hi, everyone. Welcome to 1.7, where we wrap up chapter 1, an entire chapter just on solving equations and inequalities. So in 1.1, we solved some linear equations. In 1.2, we learned to apply some of those things. 1.3, we solved quadratic equations, which we extended into 1.4, where we introduced complex numbers. 1.5, we talked about all sorts of other different types of equations we can solve, right? You see 5 different types right here. And then in 1.6, we changed gears a little bit to solve inequalities. But what we saw is that solving inequalities really isn't that different from solving equations. Different frame of reference, but really similar steps. And then in 1.7, what we're going to do, solve equations and inequalities in the same section. However, this time, all we're going to do is very briefly discuss what happens when we have absolute values. So just kind of some new rules, nothing really crazy. And you're going to see it's a lot of things we've already talked about, just a step or two of setup. So let's just start by talking about some basics of absolute value. So if we want to solve an equation that is the absolute value of some expression u equals c, where c is some constant, what we're going to do is solve u equals positive c and u equals negative c. So that comes from the definition of what absolute value really means. We don't need to, at this level, really spend time looking into the theory of that kind of thing. But long story short, if you see absolute value of u equals c, you are then breaking it into 2 equations, one of which looks identical to the original, just without the absolute value. And the other one is almost identical, except negative, whatever our constant is. So u is some expression. It's any algebraic expression, right? 5x plus 1, negative 3x plus 200, whatever it might be. And c is both a constant or an algebraic expression. So when I first mentioned it, I said, yes, this is a constant like 9 or 5, and you're going to solve an equation where it's then positive 5 and negative 5. But what ends up happening is that it works the exact same way, even if that c is another algebraic expression. It requires us to be a little careful, but otherwise it's not that different. If we have absolute value of u equals a negative constant, well, don't forget that absolute value always produces a positive number. Absolute value of 5 is positive 5. Absolute value of negative 5 is also positive 5. So there is no way absolute value of something can be negative. So there is no solution in this very specific case, right? Negative algebraic expression, that's different. A negative constant like negative 3 or negative 6, no. Like I said, absolute values can't produce negative numbers, so that's our only reason. And if we have absolute value of u equals 0, well, what you're really supposed to do is u equals 0 and u equals negative 0, but negative 0 doesn't really make any sense. Negative 0 would be the same thing as 0, so all you really need to solve is just u equals 0. So in the case where we have equals 0 on one side, we don't need to solve 2 separate equations. You're just going to set the inside equal to 0. So let's get right into it. And kind of like we saw in 1.5, when we go to apply some rules or when we go to apply some methods, we want to make sure that our absolute value, that our radical in 1.5, for example, is all by itself. So let's just start by adding 5 to both sides to get absolute value of 2x minus 3 by itself. Okay, there's supposed to be an absolute value here. I dropped that part by accident. So absolute value of 2x minus 3 equals 13. That splits up into 2 equations. 2x minus 3 equals positive 13, and 2x minus 3 equals negative 13. Again, I accidentally dropped the absolute value sign here. So this part that's highlighted right now, absolute value of this. Okay, and now what you see is, oh, that's a linear equation, and that's a linear equation. Let's add 3 in both of those 2 cases. Let's divide both of them by 2, and we get 2 solutions. negative 5 and 8. It took one real new line of setup to break one absolute value equation into two separate ones. But aside from that, not really anything different, right? Just solving a pair of linear equations, maybe a little meaty, right? 2x minus 3 equals positive and negative 13 isn't necessarily short, but I think you guys see the method here. So let's do the same thing. We got to get absolute value of 6x minus 3 by itself. So let's start by adding 18 to both sides. Then let's divide both sides by 3. Then we have absolute value of 6x minus 3 equals 9. This is what the last equation was supposed to look like. I accidentally dropped the absolute values, but that's okay. So what we're going to get is 6x minus 3 equals positive 9, and 6x minus 3 equals negative 9. And again, from here, it is exactly like stuff we've already talked about. Let's add 3 to both sides. Let's divide both sides by 6. And we get 2 answers. So absolute value equations, not really anything super insane. Some slight new steps, some slight new setup that could be very easy to forget. But I don't think there's anything here that is really blowing anybody's mind after that setup. Absolute value of x plus 3 equals 0. So what we would do is x plus 3 equals positive 0. X plus 3 equals negative 0. But at any point in your life, have you ever written negative 0? No, you haven't. So really, these two equations are one and the same. X plus 3, I don't know why there's an extra x plus 3 equals negative 0 here. That might have been a mistake. So x plus 3 equals 0 is the only equation we need to solve. Negative 0 would, in a sense, be the same as 0. All we're doing is solving x plus 3 equals 0. Subtract 3 on both sides, and we get only one answer. And that makes sense because if we want the absolute value of something to equal 5, well, the absolute value of 5 is negative 5, and the absolute value of negative 5 is 5. However, the only thing whose absolute value is 0 is 0. So it makes sense that there's only one possibility there. Same thing, absolute value of 4x minus 7 equals 0. Well, all we need to know is when the inside is 0, we're going to add 7. We're going to divide by 4. And I think this is pretty okay. So I know I'm moving kind of fast. I don't think any of the steps here are really screwing with anybody's mind. Okay. Now, 400x minus 1. The absolute value of 400x minus 1 equals negative 1. Well, don't forget, absolute values only produce positive numbers. They can't produce negative numbers. So in this case, there would be no solution. There's absolutely nothing whose absolute value is negative 1, so there's no solution. Okay, that's a pretty easy way to jump. That's kind of like what we did for square roots and even roots when it came to negative numbers. Now, I just want you to be careful because just because one side is negative doesn't necessarily mean the equation will fail. So for example, if we have absolute value of 400x minus 1 minus 2 equals negative 1, well, all we need to do is add 2 to both sides, and now it's positive. Same thing, if we have negative on the outside, we can divide both sides by negative 1. Oh, and look at that. Just because one side is negative, make sure that there's nothing you can do to change it to be positive, right? Simple algebra like that could change you from, doing a problem that you think has no solution to a problem that has a solution. And it could also be the other way around too, right? If this was a positive 1 and this was positive 2, you subtract 2 on both sides and then you would get negative 1. So that would be no solution. But not to get too deep. So just to solve that equation, we want to solve 400x minus 1 equals positive 1, and 400x minus 1 equals negative 1. Let's add 1 to both sides. Let's divide both sides by 400. Well, 2 over 400 would just be 1 over 200. 0 divided by 400 is just 0. So we get 2 solutions there. Okay, now was all true for when the thing on the right-hand side is a constant, like 1, like 9, whatever it might be. But I also told you that it functions the exact same way, even if we have an expression on the right-hand side. So let's do just that. All this is instead of just making it a positive constant and a negative constant, all we're going to do is say 2x minus 1 equals itself, x plus 5. and 2x minus 1 equals negative the whole thing, x plus 5. So just, it doesn't really, mean so much for numbers when we say 9 and negative, parentheses 9, where we really write that parentheses 9, but it does make a very big difference when we're talking about, expressions. So be careful. It's not just negative x plus 5. It's the whole thing, negative x plus 5. So we have to distribute a negative sign. And now we have two equations again. Just got to be careful because they're going to be solved a little different. Over here, let's subtract x on both sides, whereas this one we're going to add x to both sides. Well, 2x minus x is just 1x. 2x plus x is 3x. Here we're going to add 1. Here we're also going to add 1. And then one more step for the rightmost one. We're just going to divide both sides by 3. So there we go. Again, not all that different when one side is an expression. Just be a little careful. Use parentheses. They are free. Let's do one more like that. Absolute value of 3x minus 4 equals 2 times x minus 1. So what we're going to do is 3x minus 4 equals itself 2x minus 1. And 3x minus 4 equals negative 2x minus 1. You could put another set of brackets or parentheses around these two if you want. It would end up just creating another step for you. But if that helps you see the difference, by all means, go for it. Here, we're going to distribute just positive 2. But here, we're going to distribute negative 2. All right. Here, we're going to subtract 2x. But here, we're going to add 2x. 3x minus 2x is just x, but 3x plus 2x is also just x. We're going to add 4 to both sides in each separate equation. And last but not least, we just need to divide by 5 on the right. And there we go. 2 answers. So constants or expressions make one side positive, make the right side positive, then make a separate equation where the right side is negative. That's it for both constants and expressions. Okay, what about the case where we have absolute value of u equals absolute value of v? We have a double absolute value. Well, let's apply with the rules that we have created, but let's apply them twice. And what I mean by that is we would drop this absolute value sign if we made this one positive and this one negative. I don't know why why does it keep doing that? Okay, Zoom has been giving me a hard time for whatever reason on this slide. In 2 takes of recording this, it's bugged out on this slide. So I got to talk through it. Forgive me that it's not, we're not doing it in presentation wise, but here we go. So if we wanted to drop this absolute value sign, what we know is that we're going to just drop the absolute value of u, but keep the one side as itself, right? That was kind of like 2x minus 3 equals positive 9, just leaving it just like itself. But then we also solved another equation where the right side is the negative version of itself. Okay, well, that's not so crazy so far. And if we want to drop this absolute value of v, we will keep this side itself and then solve a separate equation where that side is negative itself. And same thing for over here. If we want to drop this absolute value sign, make one side positive and make one equation negative. All right, so we get 4 equations and you would think, oh no, double absolute value, we got to solve 4 equations. Actually, not quite, because these 4 equations are really 2 equations. So what if we divided both sides by -1 in this equation? And what if we divided both sides by -1 in this equation? So that's what I do here, and that's what I do here. Okay, well, when we do that, negative u over -1 is positive u. V divided by -1 is negative v. Negative u divided by -1 is positive u. Negative v divided by -1 is v. Now, we still have 4 equations, but notice something. U equals v and u equals v. Oh, this second equation we got in the second case is actually redundant. And same thing here. We had u equals -v, and we also got a redundant answer here. So guess what? Just like we've been solving every other equation, even when you have double absolute value, all you're solving is u equals positive v and u equals negative v. And as always, check your answers. Okay, so if we have absolute value of x minus 1 equals absolute value of x plus 5, again, one equation, one side is going to be x minus 1 equals positive version of the right-hand side, and the other one is going to be x minus 1 equals negative, the right-hand side. Again, use parentheses, be careful, and also notice not really all that different from things we've already done, but also if you wanted to apply that, make one side positive, make one side negative, where you keep x plus 5 the same, you can do that too and say, oh, x plus 5 equals x minus 1, x plus 5 equals negative x minus 1. So you could technically flip one side as long as you stay consistent. So here we're just going to distribute negative 1. Over here, we're going to subtract x on both sides, and over here, we're going to add x to both sides. Well, kind of strange over here. X is going to cancel out on both sides, but on this one, x plus x is going to be 2x. Well, we got an equation here that makes no sense. That's totally fine. That means we're just going to solve this one. Add 1 to both sides. Let's divide both sides by 2. And we get negative 2. So just because we got one equation that made no sense doesn't mean the whole thing fails. It just means our only solution is coming from the second half. And that's totally fine. Let's do it one more time before we get into inequalities. So we have double absolute value, but again, all it is, one version says just drop the absolute values. Right side is positive or itself, and right side is the negative version of itself, right? It's been the same thing over and over and over again. Okay, we're going to distribute negative 1. Over here, we're going to subtract 6x on both sides. Over here, we're going to add 6x to both sides. Well, 3x minus 6x is negative 3x. 3x plus 6x is 9x. Let's add 2 to both sides. Let's divide one side or one equation by negative 3 on both sides. Let's divide the other one by 9 on both sides. And we get 2 answers again. And that brings us to inequalities. So solving inequalities is kind of putting everything we've talked about in this chapter together, right? Now, not necessarily going to use, properties we talked about in 1.1, but we are going to need to solve linear inequalities, which were like linear equations from 1.1. So putting together a bunch of different things we've talked about, from absolute value and equations and all sorts of different stuff. Essentially, putting together all of these things about inequalities and absolute values, we get 4 rules, which are kind of like 2 rules. But instead of going through all the theory to end up at these results, let's just show them off. If you have absolute value of u is less than c, we convert this to another inequality that says negative c less than u less than c. That's a compound inequality. So if you have something that looks like this, immediately jump to this. That's it. Don't try and do too much. Likewise, if it's less than or equal to, guess what? Same thing, but less than or equal to signs. Now, it's a little different from when we have a greater than sign. When we have a greater than sign, this becomes an or type of inequality. So we have regular version itself and make one side negative. But, when we made things negative, when we multiplied or divided by negative numbers, we had to flip the sign. So that actually happens here as well. So equations, we don't flip equation symbols, but when we do this for inequalities, when we make one side negative, flip the sign for that negative side, and same thing for greater than or equal to. So you might notice that these 2 rules are very similar. These 2 rules are very similar. So it's kind of like 2 things to remember, but really 4 separate rules since those inequalities are indeed unique. Okay, so 4x minus 1, absolute value of 4x minus 1 is less than or equal to 9. What we're going to do is use this rule right here. Absolute value of 4x minus 1 is less than or equal to 9 would be make this negative 9 less than or equal to 4x minus 1 less than or equal to 9. And now it's an inequality we solved in the last section. We're going to add 1 to everything, not just one part. Add 1 to everything, divide everything by 4. And now everything between -2 and 5/2, including -2 and 5/2, brackets around them. That's it. Not crazy, nothing scary. Absolute value inequalities. Yes, it's a very different setup from what we had for equations, but it really isn't anything different. Let's do it for greater than when it becomes an or. Okay, well, or when we have greater than, we split it up into just itself without the absolute values, and then we do itself, flip the sign, and make it negative. Okay, there you go. Well, now we have two linear inequalities. Let's add 8 to both sides. Let's divide both sides by 2. Let's write each of those as intervals. And now, since we're dealing with or, we're taking the union of those things. So, absolute value inequalities, not really crazy, not much new from 1.6. If you still need help solving ands and ors, check out the 1.6 video. Alrighty, absolute value of 3x minus 2 is greater than -5. Well, absolute values always produce positive numbers. Well, if they always produce positive numbers are always greater than -5. So this statement is always true. Our solution set for solving inequalities would be all real numbers, -infinity to infinity. No matter what you plug in, this statement, this inequality will always be true. Absolute value of 5x plus 3 is less than or equal to -2. Well, absolute value expressions always produce positive values. So this statement is never true. If this is always positive, there's no way a positive number can be less than or equal to -2. In this case, no solution. That's it. So that's the end of 1.7. Like I said, 1.7 moves kind of fast. It's a nice summary of all the different tools, some of the different tools that we've talked about in chapter 1. And yeah, that leads us into chapter 2, where we really start to talk about functions and a lot of function properties. But without the ability to solve equations or inequalities, we can't talk about a lot of the different properties that we will discuss in chapter 2. So I will see you in chapter 2, and yeah, bye.
Hi everyone, thank you so much for watching. I hope this lecture helped and that you learned something. Just wanted to give the brief disclaimer that this lecture for this section is based on and adapted from the section in College Algebra and Trigonometry, the 4th edition by J.S. Ratty, Marcus McWaters, and Lesław Skozurpek. So just wanted to give that disclaimer. I'm not affiliated with any of the authors. I'm not affiliated with Pearson, the publisher. This is entirely a presentation and lecture I created based on the book. So thank you so much for watching, and see you in the next section.